Color, crunch, and chemistry collide in the making of the world's brightest candies. From the tiny tang of Nerds to the smooth snap of Smarties and the hard shine of Jolly Ranchers, each sweet starts with sugar science and high-speed precision. Today, we explore how these iconic treats are cooked, coated, and crystallized into the colorful confections that define the taste of childhood. Every piece of Nerds candy is smaller than a pea, lighter than a raindrop, and made with such intense precision that over 1 billion of them can roll off a single line in just one day. And while they might look like random, rainbow-colored pebbles, each Nerd is actually a layered, engineered crystal. Hard, crunchy, tangy, and wildly addictive. But the process starts with something incredibly basic: a single grain of sugar. That tiny grain is the seed. It's what every Nerd grows from. In the factory, raw sugar crystals are sifted and sorted by size. Only those that fall into the ideal micro range, small, dry, perfectly angular, make it to the next stage. These seed crystals are loaded into massive stainless steel pans that look like oversized cement mixers, tilted on an angle and constantly rotating. This is where the real transformation begins: panning. Panning is the centuries-old candy-making technique used to build layer upon layer of sugar around a center. For Nerds, it's done at high speed and microscopic scale. While the drum spins, a fine mist of sugar syrup is sprayed inside. It lightly coats the tumbling seed crystals. Almost instantly, the moisture begins to evaporate, leaving behind a thin, glassy sugar shell, but that's just the first layer. Over the course of hours, this process repeats: syrup in, drying, syrup again. Hundreds of ultra-thin layers build up, hardening each time, until a grain of sugar the size of a salt crystal becomes a tiny, oblong candy with a satisfying crunch. The panning pans are kept in warm, low-humidity rooms to control drying speed. Too fast, and the layers crack. Too slow, and the candies clump. Operators monitor texture constantly, using gloved hands to feel for stickiness or roughness. They're not just letting the machine run, they're listening to the sound of the tumbling Nerds. That soft rattle? That means the coating is hardening just right. Once the Nerds have reached their target size, and yes, every flavor is slightly different, they're ready for their first big moment of color. In a separate set of rotating pans, the candy cores are sprayed with ultra-concentrated food dye and flavoring oils. Each batch gets its own color and taste: strawberry red, grape purple, watermelon green, blue raspberry, lemonade yellow. The dyes are sprayed in fast pulses, then immediately sealed with a fine dusting of confectioner's glaze to lock in shine and prevent bleeding. If this step goes wrong, colors can mix or turn dull, so fans blow filtered air across the pans to speed drying without cooling the sugar, and operators constantly inspect samples under bright light. But here's the wild part: Nerds aren't uniform. That bumpy, irregular shape? Totally intentional. During panning, the candies grow unevenly. Some clump slightly, some roll more than others. It creates that signature texture, each piece unique, but still the same size class. No molds, no presses, no cutting. And that matters, because the final blend, the colorful jumble inside each box, is carefully calculated. In the flavoring room, technicians pour separate batches of Nerds into a multi-compartment blending carousel. Each section holds a different flavor and color. Sensors track flow rate, weight, and count. When the carousel spins, it releases a precise ratio of colors into the packaging line. This is how every box ends up with that balanced mix. Never too much grape, never too little strawberry. Now comes the packaging phase, which moves faster than the eye can follow. Nerds boxes are made from pre-printed cardboard, folded and glued by high-speed cartoners. The boxes are tiny but precise. Each must hold just the right amount of candy without crushing it or leaving too much headspace. Volumetric fillers drop the Nerds in, and a vibrating plate settles the candy for a perfect fit. Then the box flaps are heat sealed and coated with batch numbers and expiration dates. For the dual flavor Nerds, the ones with the classic split box, everything doubles. 2 separate hoppers feed into either side of a center divider, and the box is engineered with a special tab that allows you to shake out one flavor at a time. That mechanism is tested for strength and fit using robotic arms that flex and squeeze every 5th box to make sure it opens cleanly and doesn't leak. And if you've ever bought a big Nerds rope, that's a whole different line. It starts with a string of gummy, a flexible gelatin-based rope made from corn syrup, sugar, and gelling agents. As the rope emerges from its extruder, it's still tacky. That's when thousands of nerds rain down from a curtain above, sticking to the sticky surface like gravel to tar. The rope passes under gentle rollers that press the nerds into place without squashing them. Then it's cooled, cut, and wrapped in crinkly plastic at up to 200 units per minute. The entire Nerds operation is built on control. Temperature, airflow, and humidity are measured constantly. If the air is too humid, the sugar won't crystallize properly. If it's too dry, the candy can crack. Every machine is calibrated down to the millimeter. Even the rate at which syrup is sprayed is controlled by computer. Too much, and the candy melts into blobs. Too little, and it never grows. And behind the scenes, it's kept remarkably clean. Despite the sugar dust in the air and the thousands of pounds of dye in rotation, the facility is spotless. Operators wear full protective suits, face shields, and shoe covers. Equipment is scrubbed daily. Separate rooms handle allergens, and each flavor is kept in its own sealed system to prevent cross-contamination. The process may seem like chaos, bright colors, spinning drums, rattling boxes, but it's incredibly orchestrated. The noise alone is surreal. Each panning drum sounds like marbles in a dryer. Dozens spin at once, overlapping into a chorus of high-frequency clinks and low mechanical hums. There's the hiss of steam from the syrup tanks, the drone of conveyor belts, the soft hiss of powdered glaze being sprayed. It's the sound of billions of tiny candies coming to life. What makes Nerds different from other candies is how raw and elemental they are. There's no molded shape, no inner core of chocolate or nougat. They're just sugar grown into pebbles, flavored and polished. But that simplicity hides a shockingly delicate process. One batch of syrup off by a few degrees, it can throw off the entire panning schedule. A sticky drum, it clumps. Dye flow too strong, it streaks. So operators constantly tweak, test, and taste. And yes, they taste Nerds throughout the shift. Flavor uniformity is crucial. Each flavor must be bright, tart, and clean, with a crisp crunch followed by an acidic punch. Even slight deviations in acid levels, citric, malic, tartaric, can dull the flavor or make it harsh. So sensory panels evaluate every batch before it gets boxed. In the end, those tiny boxes you find at checkout counters, movie theaters, or Halloween baskets are filled with some of the most carefully grown pieces of candy on earth. No molds, no presses, just layers and layers of spun sugar, built over hours, hardened with air, colored by mist, and tumbled into the crunchy, chaotic rainbow that is Nerds. Each roll of Smarties contains exactly 15 tablets, pastel discs that weigh less than a gram each, yet hold their shape so perfectly they can survive being dropped, shaken, or sat on without crumbling. They're smooth, chalky, lightly tarred, and almost impossibly consistent. And behind that simplicity lies a candy production process that's surprisingly loud, dusty, and engineered to run with near zero waste. Smarties have been made the same way since 1949, when Edward D., a candy maker from England, moved to New Jersey and converted old pellet-making machines, designed for pharmaceuticals, into candy presses. The process still relies on compression rather than cooking. No baking, no melting, no pans of hot sugar. Just dry ingredients, blended and compacted under tons of pressure to form a candy that's hard, smooth, and somehow melts on your tongue. Everything starts with the powder blend. The recipe includes dextrose, citric acid, calcium stearate, and natural or artificial flavorings. Dextrose is the main component. It's a fine, sweet sugar derived from corn that dissolves quickly and gives Smarties their rapid, melt-in-the-mouth texture. Citric acid is what provides the sharp, fruity tang in each flavor. Calcium stearate acts as a flow agent, keeping the powders from clumping or sticking to the equipment. The flavorings and colors are added in carefully measured amounts, each one blended separately depending on the final color of the tablet. Each flavor, orange, pineapple, cherry, strawberry, grape, is mixed in massive stainless steel blenders that can hold hundreds of pounds of dry ingredients at a time. The powders look like soft pastel flour, tinted gently with color: pink for cherry, yellow for pineapple, purple for grape. These mixes are sifted to remove any lumps or foreign particles, and then loaded into holding bins above the compression line. From there, gravity takes over. The powdered candy blend is funneled into the hoppers of rotary tablet presses, machines originally designed for pressing pills. Each press consists of a rotating table filled with die cavities and a set of punches, upper and lower, aligned above and below each die. As the table spins, the punches descend and compress the powder into hard, compact tablets. No heat is used. It's purely mechanical force, tens of thousands of pounds per square inch, pressing each candy into shape. These presses are fast. A single machine can produce thousands of Smarties per minute, each tablet formed in a fraction of a second. You can hear the click-thump rhythm of punches landing hundreds of times per minute, echoing through the factory floor. The speed and pressure must be perfectly calibrated. Too much force, and the tablets crack. Too little, and they crumble in the wrapper. As the tablets are formed, they're immediately ejected onto a conveyor belt and sent to inspection. They travel under high-speed cameras and laser counters that check for missing pieces, size irregularities, and color consistency. Broken or chipped tablets are blown off the belt with puffs of air and collected for reprocessing. Ground back into powder and reintroduced into the mixing stage. The flawless tablets continue down the line to wrapping. Smarties are famously packaged in tight rolls of 15, wrapped in clear, crinkly plastic with twisted ends. That roll is another engineering feat. To begin, the candies are grouped by a gating system, mechanical paddles that count out exactly 15 tablets per drop. These tablets slide into plastic film that's being unspooled from a massive roll, moving in perfect sync. A forming collar wraps the film around the candy stack, and heat-sealing jaws bond the film edge. Mechanical fingers twist both ends of the roll, like twisting a piece of taffy at speeds fast enough to blur. It all happens without stopping. The wrapping line moves continuously, synchronized to the tablet press output. If the press slows down, the wrapping slows. If a jam occurs, say a tablet gets stuck in the chute, a robotic sensor stops the whole line within milliseconds to prevent damage or miswraps. Each finished roll is shot into a collection bin where it joins thousands of others for boxing. Depending on the final destination, Smarties rolls are packaged into retail bags, bulk boxes, or specialty gift packs. High-speed cartners scoop up rolls by the dozens and drop them into pre-folded boxes. Every package is weighed, sealed, and labeled with batch information so it can be traced back through every step of the process. But the real complexity of Smarties lies in how clean and controlled the whole system has to be. The powder used to form the tablets is extremely fine. Think baby powder consistency. Left unchecked, it can coat machines, gum up sensors, and create safety hazards. So Smarties factories use powerful vacuum systems that run continuously, pulling excess dust from the air and cycling it through filtration. Workers wear coveralls, gloves, and hairnets, and their shoes go through cleaning stations at every doorway. Even the air itself is managed. Humidity is a constant enemy in tablet candy production. If the air is too moist, the powders clump and stick. If it's too dry, static electricity builds up, which can cause inconsistent fills or attract dust to equipment. Climate control systems run year-round. keeping the production floor within a very narrow range of temperature and humidity. Every major ingredient bin is sealed and vented. The room is positively pressurized so that outside air can't drift in. And then there's flavor. Even though each Smartie is tiny, the flavor has to be concentrated and consistent. That means flavoring oils and acids must be measured down to fractions of a percent. The blending process is carefully timed. Too short, and the flavors don't distribute evenly. Too long, and the powders heat up from friction, which can cause off notes in the final candy. Each batch is taste tested during production, with sample tablets pulled from the press and dissolved in water to measure acid levels and flavor balance. And every flavor gets its own dedicated line or cleaning cycle. Because Smarties are so small, it only takes a few stray tablets to contaminate the color or taste of another batch. Between flavors, the tablet presses are completely disassembled, dies and punches removed, hoppers cleaned, dust vacuums run, and sensors wiped down. The turnaround is fast, but thorough. It's part of what lets Smarties keep their signature clarity in both flavor and color. Quality control doesn't stop with production. Once rolls are packaged, random samples are pulled from each batch and subjected to stress tests. Boxes are dropped, crushed, and shaken to simulate shipping conditions. Rolls are unwrapped and counted to confirm the exact number of tablets. Tablets are measured for diameter, weight, and break strength. And in one test, machines apply pressure from above to see how much force it takes to snap a Smartie. If it breaks too easily, the press calibration is adjusted. And yet, for all this precision, there's almost no waste. Smarties is a closed-loop operation. Any chipped tablets are recycled into powder. Any overfilled rolls are rewrapped. Even rejected wrappers and cardboard from the packaging floor are collected, shredded, and sent to recycling. The factory hums with quiet efficiency. Nearly everything that enters the system leaves as a sellable product. The result is a candy that hasn't really changed in decades, not because it couldn't, but because it doesn't need to. The pastel colors, the slight tartness, the crinkly wrapper, it all adds up to something nostalgic, efficient, and deeply engineered. And what makes Smarties different from other candies is how much is done without cooking. There's no molten sugar, no caramelization, no frying or tempering. It's all compression and control. The candy press is the heart of the process, a machine originally built for medicine, reimagined for sweetness. It doesn't just make Smarties fast, it makes them identical every single time. Jolly Ranchers are some of the hardest candies on earth. Literally. They're engineered to resist biting, built to last, and packed with so much concentrated flavor that a single piece can keep your mouth watering for 10 minutes straight. But behind each brightly colored lozenge is a high-temperature, high-speed process that turns molten sugar into razor-sharp glass with a fruit flavor punch. From raw ingredients to individually wrapped pieces, making a Jolly Rancher is a mix of thermodynamics, timing, and some very sticky science. It starts with just 3 main ingredients: corn syrup, sugar, and flavoring. Sounds simple, but the balance between those first 2 is critical. Sugar gives Jolly Ranchers their sweetness and structure. Corn syrup prevents crystallization and keeps the final product smooth and transparent. Too much sugar and the candy becomes grainy. Too much corn syrup and it won't harden properly. These 2 syrups are pumped into massive stainless steel mixing tanks, each one big enough to hold hundreds of gallons. Here, the sugar and corn syrup are blended together into a thick, pale slurry. Industrial agitators keep the mix moving constantly to prevent any settling or clumping. Once blended, the mixture is heated to over 300 degrees Fahrenheit in a continuous cooker, a machine that looks like a long metal tube wrapped in insulated coils. This step is where everything starts to change. As the temperature climbs, water begins to boil off rapidly. The mixture thickens, darkens slightly, and takes on a glossy sheen. Steam rises from the cooker vents, carrying with it the warm, sweet smell of caramelizing sugar. But unlike caramel, which cooks lower and browns more, Jolly Ranchers are heated just high enough to reach the hard crack stage between 300 and 310 degrees Fahrenheit without burning. At this point, the sugar solution becomes incredibly viscous, almost like hot lava. This is candy glass, brittle, shiny, and ready to snap once cooled. The key here is moisture removal. To get the signature glass-like hardness, the mixture must be almost completely dry, less than 2% moisture. That's why the heat is so high and why it's applied so precisely. Even a 1% change in moisture content can mean the difference between a rock-solid candy and a chewy, sticky mess. Vacuum cookers are often used in later stages to finish the dehydration process without overheating the syrup. Once the syrup hits the right consistency, it's ready for flavoring and coloring. But here's the trick. It's still blazing hot, too hot for delicate flavor compounds to survive. So the liquid is transferred to a cooling table or chilled mixing drum, where it's gently agitated and allowed to cool just enough, usually down to around 275 degrees Fahrenheit, before the flavor oils and food coloring are added. This is where things get intensely aromatic. Cherry, watermelon, green apple, grape, and blue raspberry, the iconic Jolly Rancher lineup, all rely on custom flavor blends that are surprisingly concentrated. Just a few drops per batch are enough to infuse thousands of pieces. As the oils hit the warm candy, they vaporize slightly, creating a wall of scent. Workers in this area often wear filtered masks, not because the vapors are dangerous, but because the smell is so overwhelming it can linger for hours. After flavoring, the mixture is ready to be formed, but it's still thick and sticky, like honey that's been left in the sun. At this stage, it's called the rope. The candy mass is loaded into a pulling machine, where it's kneaded and stretched in long, glossy strands. Pulling introduces tiny air bubbles and gives the candy a smoother texture and slightly lighter color. But for Jolly Ranchers, this step is minimal. They're meant to be clear and dense, not fluffy like taffy. So the pulling is short and precise. Next, the rope is fed into a forming machine. A set of calibrated rollers and dies that shape the candy into the familiar oblong lozenges. The rope passes through the rollers, which press it into molds spaced at exact intervals. Each cavity forms a single piece, cutting and shaping at the same time. The machine must keep pace with the candy's cooling curve. Too slow and the candy hardens before it's molded. Too fast and it deforms or sticks. Timing here is everything. The forming rollers run in perfect sync with the pulling speed, adjusting automatically to changes in viscosity. If the candy cools too much, the rope is reheated slightly by overhead lamps or heat plates to keep it pliable. If it's too hot, fans kick on to speed the cooling. Every second matters. Jolly Rancher syrup can go from soft to rock hard in under 10 seconds if left alone. Once formed, the individual candies ride a conveyor through a cooling tunnel. This tunnel is about 40 feet long and packed with chilled, filtered air. The candies must be cooled evenly and gradually to avoid developing internal stress, which can cause cracks or fractures later. As they travel, they harden into solid, glossy lozenges with a smooth surface and near-perfect transparency. Now comes the wrapping, arguably the most technical step of the entire process. Each Jolly Rancher is wrapped individually in a special double-layer film, waxed inner paper and a colorful printed outer film. This wrapping isn't just for branding, it's engineered to withstand extreme stickiness. Even at room temperature, Jolly Ranchers are hygroscopic. They absorb moisture from the air, which can make them tacky. The wax coating on the inner wrapper prevents the candy from fusing to the packaging, while the outer layer protects it from humidity, heat, and light. To apply the wrapper, high-speed flow wrappers align the candies with rotating belts and cutting jaws. The film is cut to size, curled around each piece, and sealed with a heated crimper that twists the ends. These machines can wrap hundreds of candies per minute, So fast, the wrapped pieces look like a blur as they shoot off the end of the line into bins. At this point, the candies are cool, hard, and shelf stable, but not yet ready to ship. They're sent through a final inspection system that uses cameras and weight sensors to catch malformed pieces, missing wrappers, or empty wrappers accidentally sealed with no candy inside. Faulty units are kicked off the line with air jets and sent to a reclaim station where wrappers are stripped and the candy is remelted. The good batches move on to packaging. Depending on the final format, Jolly Ranchers are dropped into bags, jars, or boxes. For fun-size packs, robotic arms count out a set number of wrapped candies, funnel them into plastic pouches, and seal the tops. For bulk jars, conveyors load hundreds of candies into plastic tubs, which are then lidded and shrink-wrapped. Every unit is batch-coded, dated, and weighed, and all of this happens under a strict quality protocol. If a single bag in a batch fails a weight or seal check, the entire batch is flagged for inspection. Behind the scenes, data flows constantly. Sensors track temperature at every stage, from syrup cooking to cooling tunnel exit. Viscosity is monitored in real time. Belt speeds, humidity levels, room temperature, and even air particle counts are logged. Operators monitor it all from control stations with touchscreen dashboards, ready to tweak parameters at a moment's notice. And the environment must be spotless. Sugar dust is a serious hazard in industrial settings. It's flammable, sticky, and a magnet for bacteria. So the production floor is kept under positive pressure, filtered continuously, and cleaned at the end of every shift. All machines are made with smooth, food-grade steel and designed to disassemble quickly for daily sanitation. What's perhaps most fascinating is how scalable the process is. The same basic steps: cook, flavor, form, cool, wrap, apply whether a facility is making 10,000 pieces an hour or 10 million. Everything is modular. Need to make more watermelon? Operators adjust the flavor tanks and swap in a red dye cartridge. Need to make heart shapes for Valentine's Day? Change the mold plates on the forming rollers and recalibrate the wrapping alignment. And because Jolly Ranchers are made from a solid sugar glass base, they have an almost indefinite shelf life, up to 18 months with no preservatives. That makes them ideal for long shipping routes, hot climates, and bulk packaging. It's also why they're so popular as party favors, parade tossers, vending machine fillers, and Halloween staples. But at the core of every piece is that glassy crunch, that hard, smooth texture that doesn't yield until the very end. It's not just candy, it's carefully crafted sugar architecture. The entire process is designed to preserve that structure, from the moisture level in the cooker, to the cooling curve on the conveyor, to the twist in the wrapper. Historically, gum base was made from natural tree resins like chicle, a latex-like substance harvested from the sapodilla tree, which grows in Central America. However, nearly all modern bubblegum factories now rely on synthetic gum bases. These are specially formulated blends of food-grade elastomers, resins, waxes, plasticizers, and softening agents. The use of synthetics provides far greater control over consistency, shelf life, and bubble blowing capability, which is critical for mass production and distribution. The raw materials used in synthetic gum base are delivered to the factory in large sacks or drums, and each ingredient is sampled and tested before entering the production line. Elastomers such as polyisobutylene and polyvinyl acetate provide the stretchy, elastic properties needed for bubble blowing. Resins act as binders that hold the gum together. Waxes like paraffin and microcrystalline waxes are added to soften the mixture and give the gum its pliable, non-brittle chew. Plasticizers such as glycerol, esters improve texture, while fillers like calcium carbonate or talc give the gum body and density. Each of these materials must be prepared for mixing. Solid components are broken down using industrial grinders and micronizers to achieve a uniform particle size, which ensures even distribution throughout the base. Waxes and resins are often pre-melted in jacketed stainless steel tanks equipped with indirect heating systems to prevent scorching. The raw elastomers are delivered in dense, rubbery blocks that are cut down using industrial dicing equipment before being added to the mix. Accuracy in measuring each component is vital. The slightest deviation in the amount of resin or wax can drastically alter the final chewiness and bubble-forming capability of the gum. Now it's time for the blending of the gum base, which happens in large Sigma blade mixers, named for their two interlocking Z-shaped blades that rotate in opposite directions to fold and knead heavy materials. These mixers are specifically designed to handle high viscosity compounds like gum base. The various pre-measured ingredients are added to the mixer in a specific sequence. First, the elastomers are introduced and given time to soften and break down under shear force. As they begin to form a uniform mass, resins are added to bind the structure. Waxes and plasticizers follow, blending smoothly into the mixture to help reduce internal friction and improve processability. This mixing process is not quick. Depending on the size of the batch and the recipe, the blending cycle can last anywhere from 45 minutes to several hours. The mixer itself is equipped with internal thermocouples to continuously monitor the temperature of the mass, which is maintained between 60 degrees Celsius and 90 degrees Celsius. Too low and the materials won't melt and blend. Too high and thermal degradation could occur, affecting the safety and performance of the gum. Operators observe the process through viewing ports and rely on torque readings and viscosity data from the mixer's internal sensors to determine the exact moment the gum base is fully homogenized. Once the gum base has reached the correct consistency, it is discharged from the mixer. This is a challenging step because the base at this point is extremely thick, sticky, and hot. To facilitate removal, the bottom of the mixer opens hydraulically and the heavy base is dropped onto a large stainless steel cooling table or fed directly into a sheeting system. The cooling table is actively temperature controlled using circulating chilled water to begin lowering the temperature of the gum base as quickly and evenly as possible. Large Teflon-coated rollers may be used to flatten the mass slightly, increasing surface area and speeding up the cooling process. The goal at this point is not to bring the base down to room temperature entirely, but to reduce its temperature to a workable range, usually between 40 degrees Celsius and 50 degrees Celsius, so it can move to the next stage without sticking to equipment or losing its plasticity. The partially cooled gum base is then cut into manageable blocks using high lubricity heated cutting blades. These blocks are weighed, labeled with batch numbers, and either sent directly to the next phase of production or stored in temperature-controlled holding rooms for later use. Even in this early stage of production, quality control is already an active part of the process. Samples of gum base are collected from each batch and taken to the plant's in-house laboratory, where technicians test them for elasticity, tensile strength, softness, and melt behavior. Specialized equipment such as rheometers, durometers, and texture analyzers are used to measure mechanical properties under simulated chewing conditions. This ensures that the gum base will respond correctly when blended with sweeteners, flavors, and colors in the next stages of processing. It's also worth noting that not all gum-based formulations are the same. For bubblegum specifically, the formulation includes higher levels of elastomers and plasticizers than in chewing gum intended for long-lasting flavor or dental benefits. Bubblegum is designed to be more pliable and capable of trapping air, so it can form large bubbles without breaking too easily. This performance requirement influences everything from ingredient selection to mixer settings and even downstream cooling methods. Therefore, each variation of gum base may require its own unique process settings and equipment parameters. In the next stage, the base will be transferred into another high-capacity mixer. This time, designed to handle not only dense material, but also sensitive flavor components and volatile sweeteners. The balance of heat, pressure, timing, and sequencing here is critical. Too much heat can break down sugar molecules and destroy flavor integrity. Too little, and the gum won't mix properly. The entire system must operate like a symphony of mechanical precision and food engineering science to ensure that every piece of bubblegum delivers the iconic chew and flavor burst that consumers expect. With the gum base now fully prepared, cooled, and tested, it's time for one of the most critical stages in bubblegum manufacturing: the integration of sweeteners, softeners, and flavorings. This is where the bland, rubbery core transforms into something enjoyable and familiar. The sweet, fruity, chewy product capable of inflating into perfect pink bubbles. At this point, the gum base is still a nondescript mass, pliable, tacky, but utterly flavorless and unappealing. The magic is about to happen in an industrial mixing process that must blend these next components evenly while preserving the precise texture and chew required for successful bubblegum performance. Before anything is added to the gum base, it must be brought back to a specific working temperature. Though the blocks were cooled after being discharged from the original base mixer, they must now be re-softened for further blending. This is accomplished using a series of jacketed holding vessels or warming conveyors that apply gentle, indirect heat, usually via hot water or steam circulating through double-walled stainless steel pipes. The temperature is carefully raised to a range of 40 degrees Celsius to 60 degrees Celsius, just enough to make the gum base pliable again without overheating or causing degradation of any of the soon-to-be added ingredients. The re-softened gum base is then introduced into a second type of mixer, often a horizontal batch mixer or a planetary mixer specifically engineered to process high-viscosity food materials. These mixers are outfitted with double sigma blades or paddle arms capable of kneading the gum base with immense force. Once the gum base begins to rotate and fold, the sweeteners are added gradually. These include powdered sugar, also known as icing sugar, glucose syrup, and sometimes corn syrup solids. Each of these sweeteners serves multiple purposes. Powdered sugar provides bulk, texture, and long-lasting sweetness. Glucose syrup contributes a softer mouthfeel and prevents crystallization. Corn syrup solids help maintain chewiness and shelf stability. In some formulations, especially those designed for sugar-free bubblegum, bulk sweeteners such as sorbitol, xylitol, or mannitol are used in place of sugar. These polyols require different handling due to their moisture absorption characteristics and sensitivity to heat. In any case, each type of sweetener must be fed into the mixer in stages, allowing the gum base to fully absorb and integrate the new material before more is added. This prevents clumping and ensures that the resulting mixture remains smooth and pliable. Industrial-scale screw feeders or vacuum conveyors may be used to introduce these ingredients directly into the sealed mixing chamber to maintain cleanliness and prevent contamination. Following sweetener addition, softeners such as glycerin and vegetable oils are introduced. These materials are essential to prevent the gum from becoming brittle over time and to give it the desirable, soft, elastic texture that bubblegum is known for. The quantity and timing of softener addition are precisely calculated. Too little and the gum will harden quickly after production. Too much and it will become greasy and sticky, especially under warm storage conditions. Glycerin, in particular, helps trap moisture within the matrix of the gum and acts as a plasticizer, allowing the final product to retain its chew even after prolonged shelf life. Once the bulk of sweeteners and softeners are integrated, it's time for one of the most delicate and carefully timed steps in the entire production line: the addition of flavorings and colors. Flavor compounds used in bubblegum are typically a blend of fruit, esters, vanillin, and long-lasting artificial flavors engineered specifically for gum applications. These flavors must be oil-soluble and thermally stable, as any degradation can result in bitterness, loss of intensity, or altered taste profiles. The most iconic bubblegum flavor is a blend of banana, cherry, cinnamon, clove, and wintergreen, artfully balanced to create that familiar pink taste that people associate with classic bubblegum. These flavoring compounds are often concentrated liquids or emulsified pastes, and they're introduced in the final stages of mixing to preserve their volatile aroma compounds. If added too early, the heat and shear of the mixer could evaporate or chemically alter them. The flavors are poured in slowly while the mixer runs at a reduced speed, allowing gentle incorporation. Some manufacturers use pre-encapsulated flavor beads that dissolve slowly during chewing, extending flavor release over time. Coloring agents are added simultaneously or immediately after. These are usually food-grade dyes, such as Red 3 or Red 40, depending on regional regulations, and are added in liquid form or as pre-dispersed powders. These colorants are not just about visual appeal, they help consumers identify and associate flavor with appearance. For classic bubblegum, the universal hue is a bright bubblegum pink. The dye must be evenly distributed throughout the batch, and to do this effectively, the mixer must achieve total homogeneity without overworking the gum or exposing it to heat that could cause the color to fade or change. During this final blending stage, the entire gum mass is constantly monitored. Operators inspect the mixture for uniformity, gloss, elasticity, and color consistency. Samples may be extracted from the mixer at regular intervals and manually kneaded or stretched to ensure no streaking or spotting. Texture and pliability are tested by compressing and stretching a small piece by hand or using mechanical texture analyzers. If any inconsistency is found, whether it's too stiff, too soft, uneven in color, or lacking in flavor, the batch may be reprocessed or scrapped entirely, depending on the deviation severity. Once the gum reaches the desired final formulation, it's discharged from the mixer onto a temperature-controlled rolling table. At this stage, the gum has taken on its familiar look and feel: soft, elastic, vibrantly colored, and bursting with aroma. However, it's still a massive block of uncut material, far from the small, uniform pieces sold in stores. To prepare it for shaping and portioning, the gum is flattened using motorized rollers that compress it into thick sheets. These rollers are heated just slightly, enough to keep the gum pliable, but not so hot that it becomes sticky or begins to sag. The sheeted gum is then conveyed into a sizing line, where it passes through multiple sets of progressively narrower rollers to reduce the sheet thickness to the exact target for the final product. Whether the gum will be cut into strips, rolled into tape, molded into spheres, or formed into pillow-style pieces depends on the final product format. The sheet thickness must be precise, too thick, and the gum will be too large to chew comfortably. Too thin, and it will tear or lack substance. Precision slitter blades then slice the gum into long ribbons, which are cooled again on conveyor belts using ambient air or chilled tunnels. These ribbons are stacked and allowed to rest briefly in temperature, tint, and humidity controlled zones. This rest period, sometimes called the conditioning phase, allows moisture and elasticity to equilibrate across the entire piece of gum. It helps stabilize the internal structure and prepare the gum for cutting, shaping, and packaging without causing cracking or deformation. At this point, bubblegum is fully formed in its raw shape, but still unwrapped and unpackaged. The product is ready for the next phase, which involves high-speed forming machines, wrapping systems, and final packaging lines designed to handle thousands of pieces per minute. These systems require their own precise engineering and synchronization to maintain the integrity and appeal of the final product. Now that the bubblegum has been properly flavored, colored, sheeted, and rested, it enters one of the most mechanically intricate and visually satisfying stages of production: shaping and cutting. At this point, the gum exists in long, flat ribbons of pliable, glossy material, carefully rolled and stacked in conditioned zones to ensure uniformity and stability. These ribbons are conveyed in single file onto a forming line that uses high-speed, synchronized mechanisms to turn raw sheets into the iconic forms consumers recognize, whether small pillow-style pieces, sticks, chunks, tape rolls, gumballs, or extruded logs. Let's first explore the most common format, the pillow-shaped bubblegum piece. This format is familiar from vending machines, Halloween candy mixes, and individual wrappers. To achieve this, the bubblegum ribbon is fed into a forming wheel, where it is gently guided through a series of progressive molds or cavity rollers. These rollers are designed with alternating male and female cavities that press into the gum from both sides, creating the shape of a small rectangular block with softened edges. As the ribbon passes through these molds, the gum is compressed and cut simultaneously by a synchronized die cutter positioned just after the final molding wheel. Cutting must be done with extreme precision, as even a millimeter of deviation could affect packaging alignment and product weight. To account for thermal expansion and gum elasticity, the cutting blades are adjustable in both depth and cycle timing. High-speed optical sensors detect the flow rate of the gum ribbon, feeding data into a digital controller that dynamically calibrates the cutter's speed in real time. The gum, now formed into uniform bite-sized pieces, is ejected onto a short conveyor, ready for wrapping. In the case of bubblegum stick formats, like the flat rectangular pieces found in classic packs, the shaping process is slightly different. Instead of molding with rollers, the gum sheets are trimmed on all four edges to create clean, sharp lines. They are then passed through a rotary cutter equipped with hardened steel blades, slicing the sheet into strips of exact dimensions. These strips are stacked and cut again to create individual sticks. The machines responsible for this operation resemble guillotines, but with servo-controlled precision that allows for continuous, non-stop operation at high speeds. The final sticks are conveyed into wrapping units without any manual handling, preserving hygiene and maintaining throughput. Bubblegum tape, a novelty format often rolled into small plastic canisters, requires its own unique process. The sheeted gum is passed through a winding station where it is gently rolled into a flat coil, not unlike a roll of tape. Tension is carefully controlled here, too much pressure, and the coil will deform or stick to itself. Too little, and it will unravel inside the container. Once coiled, the tape is automatically dropped into a custom-formed plastic shell, usually hinged with a pop-top lid. A blade inside the lid allows consumers to tear off a desired length. These plastic cases are injection molded on-site or sourced in bulk and fed into the filling line by vibratory bowl feeders. For gumballs or spherical bubblegum formats, the production method is even more specialized. Instead of being formed from ribbons, these are made using extrusion and spheronization techniques. Warm gum is extruded through a nozzle into a thick rope, which is then cut into small segments by a rotating knife. These segments are dropped into rotating pans, lined with friction-inducing surfaces that tumble the gum continuously, rounding the pieces into spheres through centrifugal motion. Once the balls reach a near-perfect shape, they are cooled and coated in a separate process, which we'll explore shortly. Regardless of the final shape, all bubblegum formats at this stage are unwrapped and uncoated, meaning they are vulnerable to sticking, moisture absorption, and contamination. Therefore, the next critical phase is the wrapping and packaging process, which combines high-speed automation, material engineering, and branding considerations. Starting with pillow pieces and sticks, the gum is immediately conveyed into primary wrapping machines. These are high-speed horizontal or vertical flow wrappers, capable of wrapping hundreds of pieces per minute. A continuous roll of printed film, typically made of polypropylene or foil-backed paper, is unwound and fed through the machine. As the gum pieces travel along a conveyor, The film wraps around each piece and is sealed using heated crimpers that create a back fin seal and two end seals. For some classic styles, twist wrapping machines are used instead, which pinch both ends of a small rectangular wrapper and twist them tightly around the gum. These machines are equipped with sensors that detect gum position and length, ensuring perfect alignment between the product and its printed branding. If even a single wrapper is misaligned or improperly sealed, that piece is ejected from the line via pneumatic diverters. Wrapped pieces are then collected, counted, and transferred in bulk to secondary packaging machines. Secondary packaging is where individual units are grouped for retail sale. For stick gum, this may involve stacking 5 or 10 wrapped sticks into a flat paperboard sleeve, then shrink wrapping the pack. For pillow gum, machines automatically count the desired number of pieces and drop them into a pre-formed bag, which is then sealed using heat or ultrasonic welders. Packaging films are chosen for durability, oxygen resistance, and visual appeal, and often include tear notches or resealable zippers for convenience. In the case of bubblegum tape, filled plastic canisters are labeled and moved through a shrink sleeve applicator, which places a heat shrink label around the container. This sleeve serves both branding and tamper-evident functions, and is tightened using a controlled burst of steam or radiant heat. Finally, canisters are packed into display boxes or larger cartons using robotic pick-and-place arms. Now we return to gumballs, which undergo a unique finishing step: sugar coating. Unlike other formats, gumballs are coated in a hard, shiny shell that not only protects the gum inside, but also adds flavor, color, and gloss. This process is performed in large stainless steel coating pans that slowly tumble the gumballs while successive layers of syrup and powdered sugar are applied. The syrup typically contains water, glucose, and food coloring, which adheres to the surface of each gumball. Then a layer of sugar or sugar alcohol-based powder is sprinkled over the syrup, sticking to it and gradually building up a thick shell. Each coating layer must be dried before the next is added. Warm air is blown gently into the pans while the gumballs tumble, ensuring even drying without cracking or warping the shell. After multiple layers are built up, sometimes more than a dozen, the gumballs are ready for polishing. This final step involves applying a thin layer of food-grade wax or shellac to the gumballs to create the glossy, reflective finish that's so iconic. The polished gumballs are then cooled, inspected, and fed into bulk bagging or capsule dispensing systems depending on their final use. Throughout the forming, wrapping, and packaging process, real-time quality control continues at every junction. Vision inspection systems verify wrapper alignment, seal integrity, and color consistency. High-speed checkweighers ensure that every package contains the correct number of pieces and meets the stated weight. Metal detectors and X-ray systems scan for any foreign particles or processing defects. If a flaw is detected, the package is automatically ejected and flagged for review. And behind all of this automation is a digital infrastructure tracking every batch, from base production through to final packaging. Every piece of bubblegum can be traced back to the exact shift, mixer, raw ingredient lot, and even the machine operator responsible for that run. This traceability system is essential for food safety, quality assurance, and regulatory compliance. Once bubblegum has been fully processed, formed, wrapped, and inspected, it enters the final phase within the factory: storage, quality verification, and preparation for shipment. Although the gum is now finished, it still requires careful handling to ensure that its quality and integrity remain intact all the way through to its final retail destination. The post-production environment is just as controlled as the manufacturing zones. Finished goods are transferred into climate-regulated storage areas, where temperature and humidity are strictly maintained to preserve the texture, flavor, and packaging condition of the gum. Each product pallet is labeled with QR codes or barcodes that carry essential traceability information: product type, batch number, production date, and expiration code. These codes integrate with warehouse management systems that organize inventory by shelf life and destination. The warehouse operates on a strict first in, first out (FIFO) system to make sure the oldest products are shipped first, reducing waste and ensuring consistent freshness in the marketplace. Before any product is released for shipping, quality control teams perform final checks. Samples from each lot are pulled and tested for packaging seal integrity, gum softness, visual consistency, and flavor. Any package that fails inspection is flagged, and the rest of its batch is reviewed. All quality records are logged digitally, tying back to the original gum base formulation and mixing parameters. This robust traceability ensures that, in the rare event of a defect or recall, every package's full production history is instantly accessible. Once cleared, the products are palletized and prepared for outbound delivery. Some are shipped to retail distributors, others to vending machine companies, export terminals, or wholesalers. Trucks used for transport are checked for cleanliness and proper loading temperatures to ensure the gum isn't exposed to heat or humidity during transit. Stretch-wrapped pallets are loaded according to weight and stability guidelines, scanned out of the factory system, and then dispatched. Even after leaving the facility, each batch of bubblegum remains traceable, monitored, and accountable. This level of post-production oversight is essential to maintaining brand reliability and consumer trust. It ensures that the bubblegum purchased in a corner store, supermarket, or theme park tastes exactly as intended: sweet, chewy, stretchy, and perfectly made. From polymer blending and base formulation to flavor integration, shaping, wrapping, and final logistics, the entire bubblegum production process is a seamless combination of food science, mechanical precision, and quality management. It's a surprisingly complex journey for a product designed to be fun and carefree, proof that even the most playful confections are supported by a foundation of serious, sophisticated industrial engineering. The production of Hershey's chocolate, from raw cocoa beans to the smooth, creamy bars found in stores across the globe, is a finely tuned industrial process that combines traditional chocolate-making techniques with large-scale factory automation. The journey begins with the sourcing of raw ingredients and extends through roasting, grinding, conching, tempering, molding, and packaging, all carefully orchestrated to deliver Hershey's signature taste and texture in every bar. The process starts at the very beginning of the supply chain, the harvesting and sourcing of cocoa beans. Hershey sources its beans primarily from West Africa, including countries like Côte d'Ivoire and Ghana, where cocoa trees grow in tropical climates. Once harvested, the beans are fermented under banana leaves or in wooden boxes for several days. This crucial step develops the deep chocolate flavor. After fermentation, the beans are sun-dried, sorted for quality, and bagged for export. Upon arrival in the US, Hershey's manufacturing facility inspects every shipment, checking for size, moisture content, and the absence of mold or pests. The beans are then conveyed into the cleaning and sorting machinery, where they pass through vibrating sieves, pneumatic suction tubes, and magnetic separators. This removes twigs, stones, dust, and any metallic particles. The cleaned beans are stored in large silos, kept dry and temperature controlled to preserve freshness. From here, they enter the roasting stage, which is one of the most important parts of flavor development. In the roasting stage, cocoa beans are fed into large rotating drums that heat them to between 120 and 150 degrees Celsius for about 30 minutes. The temperature and duration are carefully adjusted depending on the bean variety and flavor profile desired. During roasting, volatile acids are reduced and deep chocolate notes are intensified. The process also loosens the shells from the nibs, the edible inner part of the bean. As the roasted beans exit the drums, they move into the winnowing machine. The winnowing process uses high-speed fans and friction rollers to crack the roasted beans and separate the lighter shells from the heavier nibs. The result is a large volume of cocoa nibs, the pure form of chocolate, which are then transferred to grinding mills. These heavy-duty industrial grinders reduce the nibs into a thick, brown liquid called chocolate liquor or cocoa mass. Although the term liquor might sound alcoholic, it refers here to the liquefied state of cocoa solids suspended in cocoa butter due to the heat generated during grinding. Next, Hershey separates the chocolate liquor into cocoa butter and cocoa solids using hydraulic presses. The cocoa butter is a pale yellow fat that contributes to the creamy mouthfeel of chocolate, while the cocoa solids are rich in flavor. Hershey stores both components separately in stainless steel vats. For milk chocolate, which is the company's primary product, the recipe also calls for sugar, milk, lecithin, and flavoring ingredients like vanillin. One of Hershey's defining characteristics is its use of fresh milk, a distinguishing factor that sets it apart from European chocolatiers who often use powdered milk. In fact, Hershey operates its own dairy processing facilities in Pennsylvania. The milk is condensed and cooked with sugar to form a sweet, caramelized base that's blended with chocolate liquor and cocoa butter. This mixture is the beginning of Hershey's signature milk chocolate formula. This blend is then dried into chocolate crumb, a key intermediary unique to Hershey's process. The crumb is a dry, flaky mixture of milk solids, sugar, and chocolate liquor. It's stored in silos and later rehydrated with cocoa butter and emulsifiers during the refining stage. Creating crumb allows for a longer shelf life of the milk solids and helps develop the brand's distinctive, slightly tangy, malty flavor due to controlled milk fat breakdown during the crumb formation. Next comes refining, where the crumb and cocoa butter are combined and passed through a series of steel rollers. These rollers gradually reduce the particle size of sugar and cocoa to less than 30 microns. This fine reduction is critical for achieving the smooth mouthfeel of chocolate. If particles are too large, the texture becomes gritty. Too small, and it can feel pasty or dull on the tongue. The mixture exits this stage as a smooth, semi-fluid paste, ready for the next critical transformation, conching. In the conching process, the chocolate paste is agitated in large conche machines, steel troughs with granite or metal rollers that knead, heat, and aerate the chocolate continuously for up to 72 hours. This stage allows for further evaporation of unwanted volatile acids, the smoothing out of flavor edges, and the development of chocolate's rich, complex notes. The friction in conching also ensures the even distribution of cocoa butter, giving Hershey's chocolate its desirable melt-in-your-mouth quality. After conching, the chocolate is tempered. Tempering is the controlled crystallization of cocoa butter to ensure the chocolate sets with a glossy finish and satisfying snap. Hershey employs large-scale automated tempering units that carefully heat and cool the chocolate through a series of steps, bringing it down from around 45 degrees Celsius to 31 to 32 degrees Celsius for milk chocolate. This aligns the fat molecules into a stable crystalline structure, which gives the final bar its appealing texture and helps it resist bloom, where fat rises to the surface in white streaks. Once tempered, the liquid chocolate is piped into molds. The molding line consists of high-speed stations where molds are filled, vibrated to eliminate air bubbles, and chilled using cooled air or glycol-jacketed trays. For Hershey's iconic bars, molds are embossed with the brand's lettering and evenly segmented for snapping. The filled molds travel on a conveyor through a cooling tunnel that solidifies the chocolate completely within 8 to 12 minutes. Once cooled and hardened, the chocolate bars are demolded using a combination of vacuum systems and gentle mechanical actuators that pop them out without breakage. they move immediately into the packaging area, where a series of synchronized operations wrap, seal, label, and code each bar. Hershey's uses flow wrapping machinery that envelopes each bar in a foil and paper sleeve or film, depending on the product. The wrappers are printed with batch codes, best before dates, and product tracking identifiers. Every bar then undergoes quality control, which includes weight checks, X-ray scanning for foreign particles, and visual inspection by cameras that detect surface defects. Samples from each batch are taken to an on-site lab where texture, flavor, and microbiological safety are tested. If any irregularity is found, entire lots can be isolated thanks to the full traceability built into the production system. The packaged bars are then packed into cartons and stacked on pallets by robotic arms. The pallets are shrink-wrapped, barcoded, and sent to the distribution center. Hershey maintains temperature-controlled warehouses to ensure product stability, especially during summer months or shipments to warmer climates. Pallets are loaded into refrigerated or insulated trucks for distribution to stores across the country and abroad. What makes Hershey's chocolate truly unique isn't just the equipment or the ingredients, but the balance between automation and sensory control. While the machinery ensures consistency at massive volumes, sensory panels and chocolate experts continuously evaluate flavor, aroma, and texture to ensure every bar delivers the recognizable Hershey's profile. Even at the scale of hundreds of thousands of bars per day, this commitment to flavor accuracy and quality control is what maintains Hershey's reputation in the competitive world of confectionery. From cocoa bean to final bar, the industrial process behind Hershey's chocolate is a fascinating example of how tradition and technology merge. Every step, from roasting and grinding to conching and tempering, is carefully measured, controlled, and optimized. The result is a product that is not only nostalgic for many, but is also the outcome of over a century of engineering refinement and food science innovation. Cadbury's chocolate, with its unmistakably smooth texture and rich, creamy flavor, is one of the most beloved chocolate brands in the world. Its manufacturing process, while steeped in over a century of heritage, is executed today through a blend of tradition, advanced automation, and rigorous food science. At Cadbury's major production sites, such as the iconic Bourneville factory in Birmingham, UK, every bar begins with careful ingredient sourcing and continues through precise steps involving milling, refining, conching, tempering, molding, and packaging. Across each stage, quality control, consistency, and signature taste are paramount. The first step in Cadbury's chocolate-making journey is the selection of raw ingredients. Cadbury's signature milk chocolate is made from a combination of full cream milk, sugar, cocoa butter, cocoa mass, and emulsifiers such as lecithin. Cadbury is known for using a relatively high percentage of milk solids compared to other mass-market chocolates, which contributes to its uniquely creamy flavor. For the UK and several international markets, Cadbury still uses fresh liquid milk rather than powdered or condensed forms. The milk is delivered daily to factories from nearby dairy farms, stored in chilled stainless steel silos, and constantly stirred to prevent separation. Meanwhile, cocoa beans, the fundamental ingredient in any chocolate, arrive at Cadbury's factories from West Africa, particularly Ghana, which provides a consistent, high-quality bean that is fermented and sun-dried prior to export. Upon arrival, these beans undergo detailed quality inspections before entering the factory system. They are cleaned thoroughly to remove foreign matter, dust, sticks, stones, or metal particles through a series of sieves, aspiration towers, and magnetic separators. Once clean, the beans are roasted. The roasting stage is one of the most vital steps for developing the chocolate's flavor. Cadbury uses hot air roasting techniques in rotating drum ovens or continuous flow systems, depending on the production volume. The temperature typically ranges from 120 to 150 degrees Celsius, and the roasting time can vary from 20 to 40 minutes. During roasting, the complex chemical reactions that form the Maillard compounds intensify the chocolate aroma and flavor, while also drying the beans to the ideal moisture level for further processing. After roasting, the beans are cooled and passed through winnowers, machines that crack them open and use air currents to separate the outer shells from the inner nibs. These cocoa nibs are rich in fat and flavor and form the base of both the cocoa mass and cocoa butter used in Cadbury products. The nibs are ground in heavy-duty mills to produce cocoa liquor, a thick, chocolatey paste made from pure nibs. Though liquid due to the heat generated during grinding, this liquor is made up of both cocoa solids and cocoa butter. At this point, the chocolate making process diverges depending on the final product. For Cadbury dairy milk and similar products, a crucial step involves combining the cocoa liquor with sugar and milk. Cadbury's defining feature is its use of fresh milk, which undergoes its own separate treatment. The milk is condensed with sugar in heated vacuum evaporators, producing a thick, rich liquid. This mixture is then blended with cocoa liquor and cocoa butter to create a homogeneous chocolate base. In traditional British-style chocolate making, as Cadbury does, this mixture is then dried into what is known as milk chocolate crumb. This dry crumb is unique to Cadbury and imparts a signature caramelized, malty undertone that distinguishes it from chocolates made with powdered milk or Swiss-style processing. The crumb is produced by drying the combined milk, sugar, and chocolate mixture in large drum dryers or vacuum drying systems, resulting in a sandy, dry granule that is easy to store and rehydrate in later stages. The crumb is stored in large silos until needed. When it's time to produce finished chocolate, it is remixed with additional cocoa butter, sometimes more cocoa liquor depending on the product, and emulsifiers like lecithin. This mixture is then passed through refining rollers, a series of 5 steel cylinders that reduce the particle size of the sugar and cocoa solids. The aim is to reach a uniform particle size of around 20 to 30 microns. This gives the chocolate a smooth texture without feeling gritty on the tongue. Particle size is verified using laser diffraction particle analysis systems to ensure consistency across every batch. Once refined, the chocolate enters the conching stage, named after the shell-like shape of early conching machines. This process involves mixing, shearing, and aerating the chocolate over several hours, anywhere from 4 to 24 hours, depending on the product. Conching removes volatile acids, unwanted moisture, and any rough flavor edges. Cadbury uses both traditional longitudinal conches and modern rotary conches, depending on the scale and specific chocolate formulation. During this time, the texture becomes silkier, and the flavor deepens and rounds out. Following conching, the chocolate is transferred to the tempering line, one of the most delicate and technically controlled stages in chocolate manufacturing. Tempering involves carefully cooling and reheating the chocolate to encourage the formation of stable cocoa butter crystals, which give chocolate its shiny appearance and clean snap. Improper tempering can result in chocolate bloom, a whitish, dull coating caused by fat separation. Cadbury's tempering machines operate in a closed-loop system, cycling chocolate through a precisely controlled thermal curve. Advanced digital sensors monitor viscosity, temperature, and flow characteristics to ensure optimal temper structure. Once tempered, the chocolate is ready for molding. Cadbury's high-speed molding lines pour the liquid chocolate into molds made of polycarbonate or food-grade stainless steel, depending on the product. The molds pass over vibration plates to eliminate air bubbles and ensure even distribution. The filled molds then travel through a cooling tunnel that gradually reduces their temperature to solidify the chocolate without causing stress fractures. This ensures a uniform, glossy appearance and the correct snap when broken. Demolding is performed using vacuum lifters or gentle mechanical knockers, depending on the mold shape. For filled products like Cadbury cream eggs or caramel bars, the process includes an additional step. Shell molds are created by partially filling and spinning molds to create a cavity, which is then filled with the flavored fondant or caramel using precision depositor heads. These centers are allowed to partially set before a chocolate-based layer is applied, and the molds are fully sealed, then cooled and demolded just like solid bars. Once the chocolates are demolded, they move directly to the packaging lines. Here, automated machinery wraps individual bars in foil and branded sleeves or flow wraps them in film. The packaging materials are printed with batch codes, expiry dates, and traceability data. Optical scanners and X-ray systems perform real-time quality checks, looking for surface imperfections, air gaps, or foreign matter. Any product not meeting the strict standards is ejected from the line automatically. The wrapped bars are then grouped into cartons or multi-packs, which are robotically packed into shipping cases. These cases are barcoded, palletized by robotic arms, and shrink-wrapped for shipping. Pallets are stored in temperature-controlled distribution centers until they are shipped out to retailers. The entire inventory system is managed using enterprise-grade software that tracks each chocolate bar from production to warehouse to store shelf. What distinguishes Cadbury's industrial chocolate production from others isn't just its recipe, but its integration of craftsmanship and automation. Despite being a global brand, producing millions of bars per week, Cadbury maintains tight control over flavor, texture, and appearance through every stage, from the exact ratio of milk solids to the particle size in refining and the thermal curves of tempering. Every sensor, every conveyor, and every batch record plays a part in delivering a final product that's as familiar as it is meticulously engineered. Even sustainability is built into the process. Cadbury's factories are gradually moving toward carbon neutrality, with newer systems recovering heat from roasting for use in conching, and solar panels offsetting daytime energy use. Additionally, cocoa is increasingly sourced through the Cocoa Life program, which promotes fair trade, farm productivity, and community development in West Africa. In the end, every Cadbury Dairy Milk bar is a result of over a century of refinement, rooted in British chocolate-making tradition, but carried out in some of the most sophisticated food production environments in the world. From fresh milk and raw cocoa to the purple-wrapped bar, every step reflects a balance of nostalgia and precision, heritage and innovation. Mars chocolate bars, instantly recognizable by their dark chocolate coating, nougat core, and caramel layer, are manufactured through one of the most highly refined industrial processes in the global confectionery world. While the experience of biting into a Mars bar feels simple and indulgent, the behind-the-scenes production is anything but. It requires precision control of temperatures, flow rates, ingredient ratios, and mechanical handling, executed across multiple synchronized systems in high-speed, high-volume manufacturing plants. The entire process, from raw ingredient reception to molded bars in wrapped form, is designed for repeatability, safety, and sensory consistency, ensuring every Mars bar tastes identical to the last, whether it's made in the UK, the US, or elsewhere. It all begins with sourcing the core components: cocoa, sugar, milk, glucose syrup, and fats. Mars procures its cocoa through long-term supply contracts with farms across West Africa, where cocoa beans are fermented and dried on site before being shipped to processing facilities. Sugar is sourced from sugar beets or cane, depending on the regional plant. The milk component often comes in the form of milk powder or condensed milk, chosen for stability and easier integration into industrial formulations. Mars also uses specialty fats, vegetable oils, and cocoa butter blends for different parts of the bar to achieve specific textures and melting properties. Each of these ingredients is subjected to stringent quality control upon arrival. Cocoa powder is tested for fat content, microbial load, and flavor integrity. Milk powder is checked for protein and moisture levels. Sugars are screened for crystal size and cleanliness. Once cleared, they are transferred to bulk storage systems that feed directly into the production lines through enclosed, pressurized delivery tubes to minimize contamination. The first component to be produced on the line is the nougat base, which forms the soft but chewy core of a Mars bar. Nougat for Mars bars isn't the traditional egg white variety seen in artisanal confectionery, but a carefully engineered formula based on a whipped blend of sugar, glucose syrup, hydrolyzed soy protein, and milk powder. The dry and liquid ingredients are first mixed in large batch tanks equipped with high shear mixers. The mixture is heated to approximately 120 degrees Celsius to dissolve all solids and activate syrup structure, then cooled rapidly as it enters the aeration system. Aeration is critical. The hot syrup is whipped with nitrogen gas, chosen over air or CO2 because it's inert and maintains longer shelf stability. This whipping happens in high-capacity continuous mixers equipped with rotor-stator assemblies that shear and expand the mass into a light, foamy structure. The density is controlled down to the gram per cubic centimeter using inline flow meters and laser sensors. The freshly aerated nougat is extruded onto a cooling belt made of food-grade stainless steel or polyethylene-coated fabric. The belt runs beneath a cooling tunnel where chilled air brings the nougat's temperature down to a manageable level for further layering. At this stage, it appears as an endless beige ribbon, roughly the width and height of a Mars bar. Next comes the caramel layer, which is produced in parallel and deposited directly onto the top surface of the nougat ribbon. Caramel in Mars bars is made from a cooked mixture of glucose syrup, sugar, dairy solids, and fats, brought to a high boil under vacuum to reach the right viscosity and prevent crystallization. Caramel cookers, jacketed stainless steel kettles fitted with vacuum systems, ensure that the water content is carefully reduced without burning the sugars or degrading the milk proteins. Once cooked, the caramel is pumped into a spread depositor, a mechanism that lays down a smooth, even layer of caramel over the moving nougat sheet. The temperature of the caramel during application is closely monitored, usually around 40 to 45 degrees Celsius, to maintain spreadability without melting the nougat underneath. As the composite sheet of nougat and caramel moves along the line, it enters a laminar cooling tunnel, where chilled air slowly brings both layers down to cutting temperature. This ensures that the final bar will maintain its shape during slicing. After exiting the cooling tunnel, the layered slab is conveyed to a guillotine cutter, an automated, high-speed mechanical blade that slices the continuous sheet into individual bar-sized pieces. The cutter is synchronized with the speed of the conveyor, allowing it to produce thousands of consistent cuts per hour without crushing or dragging the layers. Optical sensors track the integrity and alignment of each cut, automatically rejecting any malformed pieces before they move to the next phase. The sliced centers are now ready for enrobing in chocolate. Each nougat caramel piece is placed onto the in-feed conveyor of a high-speed chocolate enrober. This machine pumps liquid chocolate, produced from a blend of cocoa liquor, cocoa butter, sugar, milk powder, and emulsifiers, over the bar in a curtain-like flow. The bottoms are coated first by passing over a shallow chocolate bath. Then the rest is coated from the top and sides via falling curtains of tempered chocolate. The chocolate used in Mars bars is carefully tempered beforehand. Tempering is the process of heating, cooling, and reheating chocolate to create a uniform fat crystal structure, giving the coating its shine, firmness, and resistance to bloom. Mars uses fully automated tempering units that precisely control chocolate temperature to within fractions of a degree, cycling through heating coils and chilled plates in sequence before delivery to the enrober. As each piece exits the enrober, it passes over a vibration plate that shakes off excess chocolate and ensures even coverage. Some lines use air knives, streams of compressed air directed at specific angles, to remove chocolate buildup from the sides or base of the bar. The freshly coated bars then enter a cooling tunnel that runs for 15 to 20 meters, gradually reducing their temperature in controlled stages to prevent cracking or moisture condensation. These tunnels use chilled, dehumidified air at around 8 to 12 degrees Celsius. Once the chocolate has fully set, the bars proceed to the wrapping line. Here, high-speed flow wrapping machines encase each bar in metallized polypropylene film, heat sealing both ends and the back. Wrapping machines include inline printers that apply the best before date, batch number, and factory code directly onto the film. Optical scanners check each wrapper for print clarity, alignment, and seal integrity. Any bar with misaligned film or poor sealing is ejected from the line by pneumatic arms into a separate rework bin. Wrapped bars are counted and grouped into cartons, which are then sealed, labeled, and moved to robotic palletizing systems. Robots arrange cartons in predefined patterns onto pallets based on flavor, size, and shipping destination. Each pallet is barcoded and logged into Mars' ERP system for real-time traceability. Pallets are stored in climate-controlled warehouses maintained at 18 to 20 degrees Celsius and under 50% relative humidity to preserve the chocolate's shelf life and prevent bloom or fat migration. The entire production line is monitored via SCADA systems, software platforms that oversee machine parameters, product flow, and quality metrics in real time. Operators at control stations can view temperature logs, flow rates, equipment performance, and reject rates. If a sensor detects even a slight deviation, like a variation in caramel viscosity or enrobing temperature, alerts are issued and adjustments are made immediately to avoid wasting product or compromising quality. Manufacturing Almond Joy candy bars on an industrial scale begins long before any chocolate is melted or coconut is mixed. It starts with the careful sourcing and preparation of one of the candy's most iconic and defining components, the coconut. This isn't just any shredded coconut. This is a specific, moisture-balanced, finely textured variety that gives Almond Joy its distinct chewy center. Producing coconut to these specifications requires a highly controlled and deliberate process. And in modern facilities, this step alone involves extensive coordination between agricultural suppliers, food scientists, and processing engineers. The coconuts used in Almond Joy bars are primarily sourced from tropical regions like the Philippines, Indonesia, and India, where coconut palms grow in warm, humid climates and are harvested multiple times per year. The coconuts are selected based on strict criteria such as maturity, size, and oil content, all of which contribute to the flavor and structure of the final product. After harvesting, the outer husks are mechanically removed using rotary dehusking machines, exposing the inner brown shells. These shells are then cracked open using high-torque hydraulic presses or mechanical splitters, allowing access to the white coconut meat inside, also known as copra. Once separated from the shell, the coconut meat is washed in large stainless steel tanks using filtered water, sometimes with a light chlorine solution to remove any contaminants, shell fragments, or residual dirt. The clean coconut meat is then graded using high-speed rotary shredders, which reduce it into uniform strands. These industrial shredders operate at several thousand RPMs and are fitted with specialized blades designed to achieve a consistent flake size. The exact dimensions of the shredded coconut are critical. Too coarse, and the texture becomes stringy. Too fine, and it loses its chewiness. The shredded product is then passed through vibratory sieves to remove any oversized or undersized particles, ensuring each flake meets factory specifications. Once the coconut is shredded and sized, it undergoes a drying phase, designed not to fully desiccate the coconut, but to bring its moisture content into a very specific range, typically between 12 and 14%. This drying process is carried out in large belt dryers or fluidized bed dryers that blow heated air over the coconut shreds while keeping them suspended and moving, ensuring even drying throughout. Sensors embedded in the dryer constantly monitor moisture levels in real time, allowing for micro adjustments to airflow and temperature. This precision ensures that the final coconut retains its soft, moist chewiness without being wet or prone to microbial spoilage. Once dried, the coconut is cooled with ambient air and sent through a metal detection system before being packed into sterile bulk totes or drums, ready to be delivered to the candy production line. Now it's time to go into the coconut syrup blending process, where the prepped coconut is transformed into the moist, sweet filling that forms the base of every Almond Joy bar. At this stage, the dried coconut shreds are transferred from storage bins into large stainless steel ribbon blenders or planetary mixers. These mixers are food grade and designed to gently fold the ingredients together without compressing or overworking them, which would damage the texture. While the coconut is being added to the mixer, a separate part of the factory is simultaneously preparing a sugar syrup that will serve as the binder and sweetener. This sugar syrup is cooked in large steam-jacketed kettles, each fitted with agitators and temperature sensors. The syrup typically contains a blend of sucrose, corn syrup, and a small percentage of invert sugar, which helps prevent crystallization and keeps the final mixture smooth and cohesive. The ingredients are combined with water and brought to a boil, then held at a precise temperature of around 230 to 240 degrees Fahrenheit. Once the syrup reaches the desired consistency and viscosity, it is pumped through insulated transfer lines into the mixers containing the shredded coconut. The hot syrup is slowly added into the mixing chamber while the paddles rotate at a controlled speed, ensuring that every strand of coconut becomes evenly coated. This mixing step is closely monitored for torque resistance, an indirect measure of viscosity and saturation. If the mixture becomes too stiff, it indicates that not enough syrup has been added, while an overly slack consistency could suggest too much moisture. Adjustments are made in real time, either by slowing down the mixing blades or by adding additional syrup in carefully measured quantities. The end result is a glossy, dense, and aromatic coconut mixture with a smooth mouthfeel and a controlled stickiness that allows it to hold together when molded. This freshly prepared filling is discharged from the mixer into temperature-controlled holding hoppers. From there, it is fed through sanitary auger systems into the forming line, where the next phase of production begins, shaping each bar's core. But up next is the forming process, where this cohesive coconut mixture is portioned and molded into the rectangular log shape that defines the inner core of every Almond Joy. This step is handled by a specialized extrusion and forming system. The mixture is continuously extruded through a die system that determines the width and height of the log. These forming dies are custom designed for Almond Joy and produce a consistent cross-section with slightly rounded tops, ensuring a uniform bite and a reliable surface for almond placement. The extrusion head releases a continuous ribbon of coconut mixture onto a moving conveyor belt, and a high-speed rotary guillotine, timed with the conveyor's speed, cuts this ribbon into individual bar-length pieces. The distance between each cut is controlled down to the millimeter, and a sensor-based feedback system ensures that every bar is exactly the same size. After cutting, a short air blast is applied to each log to clear away any stray coconut flakes and ensure clean edges. As the bars are cut, they enter a cooling conveyor that travels through a tunnel kept at approximately 45 degrees Fahrenheit. The cooling process is essential at this point. Not only does it help the bars hold their shape, but it also stabilizes the sugar syrup binder so that the mixture doesn't slump or deform in the next step. A key consideration during this cooling stage is air humidity. If the environment is too dry, the coconut can begin to crust or dry out. Too humid, and condensation may form, which can affect downstream adhesion with the chocolate coating. For this reason, industrial humidity control units maintain relative humidity levels around 45 to 55% inside the cooling tunnel. Once cooled and firmed, the coconut logs are transferred by conveyor to the almond placement system. Each log must receive exactly 2 whole almonds, neither more nor less, positioned evenly across the top surface. The almonds used in this process are themselves the result of a careful preparation sequence. Raw almonds are sourced from large-scale growers, often in California, and are received at the factory in bulk containers. These almonds are sorted, cleaned, and then dry roasted in large convection ovens. Roasting enhances flavor, reduces moisture to less than 5%, and gives the almonds the crunch consumers expect. After roasting, the almonds are cooled and transported to a hopper above the placement system. Here, they are singulated, separated into single file, and guided into individual almond placement arms. These arms are controlled by a vision-guided robotic system that tracks the position of every coconut log in real time. Using photoelectric sensors and high-resolution cameras, the system places each almond with millimeter-level accuracy on top of the log. The almonds are pressed into the surface just enough to adhere without sinking, and an inline inspection system checks that every bar has precisely 2 almonds aligned correctly. Any bar that deviates from this standard is removed from the line for manual inspection or rework. Now it's time to go into the chocolate enrobing stage, which marks the beginning of the transformation from a basic assembly of ingredients into the finished, glossy, consumer-ready candy bar. This process involves fully coating the almond-topped coconut cores with a layer of milk chocolate. But this is no ordinary chocolate. It has been specifically formulated and tempered to provide the right snap, shine, and melt-in-the-mouth texture that defines the almond joy eating experience. The chocolate is stored in holding tanks maintained at 110 to 115 degrees Fahrenheit and stirred continuously to ensure it remains fluid and free from separation. Before use, the chocolate is tempered through a process that heats, cools, and reheats it to align the cocoa butter crystals in a stable form. Proper tempering is essential as it prevents fat bloom and gives the coating its glossy finish and clean break. The tempered chocolate is pumped into an enrobing machine, which dispenses it in a continuous curtain across the width of the conveyor belt. As the coconut and almond cores pass underneath, they are fully submerged in the falling sheet of chocolate, while a bottoming unit applies a layer of chocolate to their underside. Immediately afterward, a series of air blowers remove excess chocolate, ensuring a uniform thickness and revealing the shape of the almonds beneath. What emerges is a fully coated bar that looks and feels like the final product, but still needs time to set. That step begins as the bars enter a temperature-controlled cooling tunnel, and that's where the next phase begins. Inside the cooling tunnel, a meticulously engineered, climate-controlled chamber extending over 30 feet in length, the freshly enrobed Almond Joy bars begin their chocolate setting phase. This tunnel is one of the most crucial parts of the process, ensuring that the tempered chocolate coating transitions from a glossy liquid into a solid shell with the perfect texture and finish. The chocolate must cool at a precise rate, not too fast, which could result in cracking or sugar bloom, and not too slowly, which could cause the cocoa butter crystals to misalign, leading to dullness or fat bloom on the surface. The tunnel operates at an ambient temperature between 45 and 55 degrees Fahrenheit, and relative humidity is tightly controlled around 50%. High-efficiency fans circulate cold air evenly across all bars on the conveyor. and temperature sensors track minute variations along the length of the tunnel. The speed of the conveyor is carefully synchronized with the chocolate's crystallization curve so that the bars spend just the right amount of time cooling, usually between 7 and 12 minutes, depending on environmental conditions, line speed, and chocolate thickness. During this stage, the chocolate coating fully hardens around the coconut and almond core, creating a glossy, smooth outer layer that locks in moisture and flavor. The almonds, having been gently pressed into the top of the coconut before enrobing, remain clearly visible through the chocolate shell, creating the bar's iconic bumpy silhouette. As the bars exit the tunnel, they are now fully formed, with all primary ingredients integrated and stabilized. But the next phase, inspection and quality control, ensures that only perfect bars make it into the hands of consumers. The next step is the multi-layered inspection and quality assurance phase, a critical junction in the Almond Joy manufacturing process. Here, each fully cooled, enrobed bar passes under a series of digital scanning systems equipped with high-resolution cameras and sensors that detect inconsistencies in shape, size, and appearance. These systems analyze every bar in real time using image recognition algorithms trained to identify surface defects, incomplete chocolate coverage, missing almonds, or any signs of misalignment. Each camera system captures dozens of images per second, creating a detailed digital fingerprint of each bar. If a defect is detected, such as an air bubble on the surface, a chocolate smear, or a misaligned almond, the bar is automatically rejected using a quick puff of compressed air that directs it off the main conveyor into a designated collection tray. Rejected bars are recorded and analyzed in quality control logs to monitor trends and flag any upstream issues in real time, like syrup inconsistencies or almond placement variances. Following the visual inspection, the bars pass through an inline check weighing station. This precision balance system measures the mass of each individual bar down to the 1/10 of a gram. Bars that are even slightly under or overweight are flagged and rejected from the line. This strict weight control not only ensures product consistency and consumer satisfaction, but also regulatory compliance, as all packaged goods must meet labeled net weight declarations. These check weighers are recalibrated frequently during production to maintain absolute accuracy, and the results are logged digitally to provide traceable batch records. Next, a random sampling process is initiated where trained human inspectors pull sample bars from the line every few minutes. These samples are taken to a nearby quality assurance room for deeper evaluation. Inspectors slice open the bars and examine the cross-section for proper ingredient distribution, moisture retention in the coconut layer, almond placement, and shell integrity. Taste testing is performed by a trained sensory panel in a separate tasting room to ensure the flavor profile remains consistent. Parameters like sweetness, chewiness, and chocolate snap are all evaluated and recorded in a detailed quality report. Once bars have successfully passed through the inspection phase, they are ready for the next stage, packaging. But up next is the flow wrapping process, where each Almond Joy bar is individually wrapped using high-speed machinery designed to maintain hygiene, preserve freshness, and uphold branding consistency. The packaging film, pre-printed with the Almond Joy logo and product information, is loaded in giant rolls at the start of the packaging line. These rolls are threaded through a series of rollers and tensioners that keep the film aligned and taut as it's fed into the wrapping unit. The bars are spaced and synchronized onto a conveyor lane and fed into the flow wrapping machine, which envelopes each one in film and seals it at the sides and ends using heated crimping jaws. These jaws press the film together and apply controlled heat and pressure to create airtight seals that are strong yet easy to open. The sealing temperatures are carefully monitored to avoid overheating the chocolate within, as excess heat could cause the surface to dull or soften. Each wrapped bar is then passed under a thermal inkjet or laser coater, which prints the best before date, batch code, and production time directly onto the wrapper. This traceability information is vital in case of recalls, inventory tracking, or shelf life analysis. Vision sensors verify the presence and clarity of the code, and any missing or illegible codes trigger a rejection mechanism. The speed of this entire process is remarkable. Modern flow wrappers can handle upwards of 500 bars per minute, all synchronized perfectly to match the upstream enrobing output. Once wrapped and coded, the Almond Joy bars are grouped into retail-ready formats. Depending on the destination, this could mean twin packs, king-size versions, or standard singles in cartons. Cartoning machines fold and glue cardboard sleeves or cartons, then insert the correct number of bars automatically. These cartons are scanned for correct orientation, closed, and labeled with shipping and SKU data. A final check weigher ensures that the total weight of each carton falls within specification, and the completed units are then moved down the line to case packing. The case packing phase involves automated robotic arms or pick-and-place systems that lift finished cartons and place them into larger, corrugated shipping cases. The arrangement within each case is optimized for pallet stability and protection during transit. Each case is labeled with product identifiers, batch codes, and destination information, then sealed and conveyed to a palletizing station. Palletizing robots stack the cases onto wooden or plastic pallets in precise configurations to maximize space and maintain structural integrity during transport. Once a full pallet is assembled, it's wrapped in high tensile stretch film using automated rotary arm or turntable wrappers. This wrapping secures the load against shifting during transportation and also provides a barrier against dust and moisture. Each pallet is then tagged with a barcoded shipping label that includes tracking information, weight, and customer-specific handling instructions. The completed pallets are moved to a climate-controlled storage area within the warehouse to await shipment. Now, it's time to go into the logistics and distribution stage, where the focus shifts from production to coordinated movement and inventory management. Almond Joy bars, like all Hershey's products, are managed within an enterprise resource planning system that tracks production batches, inventory turnover, and customer orders in real time. Based on demand forecasts, pallets are selected for outbound shipment, assigned to specific trucks or containers, and scanned out of the warehouse with full digital traceability. Transport is typically handled using refrigerated trucks during warmer months, as the milk chocolate in Almond Joy bars is sensitive to heat. Temperatures are maintained between 55 and 65 degrees Fahrenheit during transit, and GPS-linked thermal loggers monitor each vehicle's internal climate from origin to delivery. If a truck deviates from its safe range, alerts are sent to both logistics managers and warehouse supervisors to prevent spoilage. Once the bars reach regional distribution centers or retail warehouses, the product is scanned into inventory and routed to store shelves. Retail partners rely on synchronized inventory systems that replenish stock as it sells, often based on point-of-sale data. The entire journey, from Coconut Grove to grocery store, can be completed in just a matter of weeks, but every phase must function flawlessly to deliver a bar that meets Hershey's standards for quality, freshness, and consistency. And even once the product hits shelves, the factory's job isn't done. Ongoing consumer feedback, seasonal demand changes, and promotional cycles influence continuous adjustments in batch sizes, production schedules, and packaging variations. Special holiday versions, multi-packs, and limited time offers are all planned months in advance and require tailored processes, new molds, and reprogrammed machinery, an impressive level of flexibility embedded within an otherwise standardized production system. Quality assurance continues to play an active, ongoing role in the manufacturing of Almond Joy, even after the bars have been wrapped, packed, and prepared for distribution. In fact, Behind the scenes of the main production line, a parallel infrastructure operates continuously to monitor, record, and validate every element of the process in real time and long after the initial production phase. This includes not only in-process checks, but detailed post-production sampling and retention, which are central to traceability, regulatory compliance, and product consistency. One critical ongoing practice is the archiving of batch samples. As bars are wrapped and prepared for shipment, dedicated staff routinely pull random samples from each batch, often one every few thousand bars. These samples are sealed, labeled, and logged with all relevant metadata: the exact time of production, line number, raw material codes, chocolate viscosity at time of enrobing, coconut moisture content, and even almond roast profiles. These reference bars are stored in secure, climate-controlled storage units maintained at conditions that mimic ideal shelf environments. The goal is to preserve these products in a stable state for up to 2 years, during which time they may be retrieved for comparison if any quality concerns or deviations arise. In addition to acting as an insurance policy against customer complaints or distributor queries, these archived samples are regularly tested as part of long-term shelf life studies. Trained quality assurance technicians perform controlled aging studies by artificially accelerating the aging process in heated chambers to evaluate how the product will hold up over time. These studies track changes in coconut chewiness, chocolate bloom resistance, almond crunch retention, and overall flavor integrity. Sensory analysis is conducted by expert panels who evaluate sweetness, aroma, textural contrast, and mouthfeel using standardized scoring systems. This data feeds back into ingredient sourcing decisions and packaging refinements, allowing the team to adjust variables well before any potential issues could reach consumers. Now, it's time to go into the digital control systems that operate silently beneath every piece of equipment, coordinating, recording, and adjusting every stage of the Almond Joy production process. At the core of this system is a network of programmable logic controllers, PLCs, which manage the real-time operation of machinery across the factory floor. These industrial computers are programmed to respond to sensor inputs and control outputs with extreme precision, enabling the synchronization of critical events such as syrup dosing, coconut extrusion, chocolate tempering, and wrapper sealing. For example, if the syrup temperature in the blending kettle falls even slightly below the optimal range of 235 to 240 degrees Fahrenheit, the PLC will automatically trigger a compensatory adjustment in steam pressure. Similarly, if a sensor detects that the chocolate curtain in the enrober has begun to thin, indicating an issue with flow rate or chocolate viscosity, the system can alter pump speed, activate an agitator, or send an alert to the line technician. These reactions happen in milliseconds, ensuring seamless operation with minimal human intervention. All this data funnels into a supervisory control and data acquisition system, or SCADA, which acts as the digital nervous system of the plant. SCADA systems provide centralized visualization of every variable in production, from torque readings in the coconut mixes to conveyor belt speeds on the packaging line. Live dashboards display real-time metrics alongside historical trends, and operators can set control limits to trigger alarms, shutoffs, or automatic corrective actions when deviations occur. Data logging is continuous, with every action time-stamped and stored in redundant backups for audit and analytics purposes. But up next is the role of continuous improvement teams and how they use this wealth of production data to fine-tune the manufacturing process. Rather than viewing each shift as a discrete operation, modern Almond Joy factories treat every minute of production as a learning opportunity. Statistical process control specialists and lean manufacturing engineers analyze massive volumes of data to identify small but significant trends. For instance, if there's a subtle uptick in the rate of chocolate flow variation on line 2 during evening shifts, it might suggest thermal drift in the tempering unit or minor calibration errors in the chocolate pump. These insights allow preventive maintenance schedules to be updated, saving time and resources while minimizing the risk of future disruptions. Some adjustments are made on the spot, while others lead to full pilot testing cycles. Pilot lines, scaled-down versions of the full production setup, allow engineers to test adjustments to temperature profiles, mixing durations, or conveyor speeds without interrupting primary operations. For example, if a new batch of coconut arrives with slightly higher fat content than normal, the pilot team may experiment with modified syrup ratios or mixing times to maintain the same moisture binding characteristics. Results are measured using laboratory tools like refractometers, rheometers, and moisture analyzers. And the most successful configuration is then rolled out to full production. The focus on fine-tuning doesn't stop at equipment and ingredients. It also extends to the behavior of the product throughout the supply chain. Some Almond Joy bars are shipped across the country or even internationally, and that means packaging and formulation must perform under a wide range of conditions. Engineers perform transit simulations using vibration tables and thermal chambers to replicate the effects of long-distance trucking or air freight. These simulations allow packaging specialists to evaluate wrapper integrity, seal strength, and chocolate stability under heat and motion stress. In cases where performance can be improved, new materials or layering structures are proposed, often months before the consumer ever sees the final package. It all starts long before the fries hit the fryer. Behind the golden arches and the crunch of each familiar bite lies a factory system of immense complexity, one that spans agriculture, chemistry, precision slicing, and global logistics. McDonald's French fries may seem like simple potato sticks fried in oil, but the reality is that each one is the end product of a deeply controlled, highly optimized manufacturing process. And what most people don't realize is how much of that process is hidden in plain sight at the factory level, where McDonald's and its contracted processors manage every microscopic detail to make sure every fry, from Tokyo to Texas, tastes exactly the same. The process begins with the potatoes themselves, but not just any potato will do. McDonald's fries are made almost exclusively from specific varieties, most commonly the Russet Burbank, the Shepherdie, the Ranger Russet, and the Umatilla Russet. These varieties are chosen for their long shape, high starch content, and relatively low sugar levels, which are crucial for creating that ideal, crispy exterior and soft interior that define McDonald's fries. What McDonald's doesn't advertise is how deeply it's involved in the agricultural side of this operation. The company works directly with contract farmers, some of whom grow nothing but McDonald's potatoes on thousands of acres of land. These farmers follow strict growing guidelines dictated by McDonald's and its primary potato processors like J.R. Simplot and Lamb Weston. Everything from the irrigation schedule to the exact time of harvest is data-driven and monitored by field agronomists. Why so much control? Because if the potato's sugar level is too high, the fry will burn in the oil, turning dark brown instead of golden yellow. If the potato has too much moisture, it will steam instead of crisping. And what's often hidden from view is the extensive sorting and testing done before the potatoes even make it to the processing plant. Once harvested, potatoes are stored in high-tech facilities that carefully regulate humidity, airflow, and temperature, often between 45 degrees Fahrenheit and 50 degrees Fahrenheit, to prevent sprouting and sugar buildup. At this stage, the potatoes go through a phase known in the industry as curing, which helps them develop a tougher skin and reach the desired sugar-to-starch balance. McDonald's factories don't reveal much about this curing phase, but it's one of the most critical elements to ensure that the potatoes will fry up properly when they finally reach your tray. When potatoes arrive at a McDonald's processing facility, many of which are run by their longtime partner, Simplot, they're subjected to a barrage of sorting and quality control tests. The first step is visual sorting, where cameras and AI-powered systems scan each tuber for defects, bruises, blemishes, and anything that would impact final appearance. Those that don't meet the exact standards are removed. But what most people don't know is that the internal sugar content of the potato is also tested using sophisticated near-infrared scanners. Potatoes with sugar levels, even slightly outside of spec, are rerouted to other uses or discarded entirely. After sorting, the potatoes are cleaned in an intense, multi-stage washing process. They pass through flumes, essentially water slides, where dirt and debris are blasted away by high-pressure jets. Then, they're scrubbed mechanically in abrasive drums and visually re-inspected. By the time a potato reaches the peeling phase, it's already undergone more inspections than most food products receive in their entire life cycle. Why? Because McDonald's doesn't just want quality, they want standardization. Each fry must look and taste the same, regardless of whether it's cooked in Malaysia or Montana. Peeling is done using a high-pressure steam system. The potatoes are loaded into a sealed vessel and blasted with superheated steam for just a few seconds. This causes the skin to loosen rapidly. As soon as the pressure is released, the skins separate and are rinsed away. What remains is a completely peeled, pristine potato ready for slicing. But the slicing is not random. It's done by a process far more mechanical and mathematical than most people would guess. The peeled potatoes are shot at extremely high speeds, up to 60 miles per hour, through a grid of stainless steel cutting blades known as a water knife. These blades slice the potatoes into precise lengths and widths, typically around 0.28 inches thick and up to 3.5 inches long. The water jet ensures minimal friction and deformation, which is especially important for keeping the fries straight and uniform. In the background, software algorithms are constantly adjusting cutter feed rates and blade sharpness to match the physical properties of each batch of potatoes. But here's where the first secret really kicks in. Once the fries are cut, they don't go directly into oil. First, they're blanched in hot water, typically between 160 degrees Fahrenheit and 170 degrees Fahrenheit, for several minutes. This is a crucial but rarely discussed step. The blanching process serves multiple purposes. It removes excess sugars to reduce browning during frying. It gelatinizes some of the starches to create a smoother exterior. And it partially cooks the interior to ensure the fry finishes with the right soft texture after final frying in store. What's less known is that this water may be treated with additives, like citric acid or sodium acid pyrophosphate, to preserve the color of the fries and prevent graying during storage. After blanching, the fries are rapidly dried in a high-powered air system. This air drying tunnel removes surface moisture to prepare the fries for the next step, the first fry. Yes, that's right. McDonald's fries are fried twice, but the first time doesn't happen in your local restaurant. It happens at the factory. The pre-frying phase is done in massive vats of vegetable oil, heated to around 375 degrees Fahrenheit. The fries are cooked for just 45-60 seconds, long enough to create a light outer shell, but not to fully cook the interior. This brief fry locks in the shape and starts forming that distinct McDonald's fry texture. After this flash fry, the fries go straight into a blast freezer. In a matter of seconds, their temperature is dropped from over 300 degrees Fahrenheit to well below 0 degrees Fahrenheit. This locks in moisture, halts cooking, and extends shelf life for months. The result is what's known in the industry as a par-fried product, partially cooked, frozen, and ready to finish. Once the freshly par-fried McDonald's fries exit the industrial fryers, still golden but only partially cooked, they enter one of the most carefully engineered steps of the entire production process: freezing. This phase is far from ordinary. The secret to locking in that signature McDonald's fry texture and color involves cryogenic speed, airflow science, and microcrystal management. Every fry is treated not as a raw potato product anymore, but as a finished structure in progress, one that must be preserved in a state of suspended readiness until it is reanimated in the deep fryers of restaurants across the globe. The fries are conveyed directly from the oil fryers to a blast freezing tunnel. This isn't your average cold room. It's a highly pressurized, continuous flow freezer capable of dropping product temperature from over 350 degrees Fahrenheit to well below 0 degrees Fahrenheit in less than 5 minutes. This rapid freezing is key to quality preservation. Why? Because fast freezing forms tiny ice crystals within the fry's cellular structure. These microcrystals are less damaging than larger, slower formed crystals that rupture cell walls and lead to mushy textures when cooked. McDonald's suppliers invest heavily in ultra-fast freezing systems to ensure that every fry maintains its structural integrity from factory to fryer. Inside the freezer, conveyor belts carry fries through multiple zones where the temperature is dropped in controlled increments. Powerful fans circulate ultra-cold air in a laminar flow pattern, creating a uniform freezing effect across each fry's surface. Sensors inside the chamber measure air velocity, temperature, product thickness, and moisture levels to adjust fan speeds and refrigerant input in real time. The goal is a fully frozen product with a moisture content that stays just right. Not too dry, not too icy, so that the final fry will puff and crisp just the way McDonald's demands. But before these frozen fries are boxed and shipped, one more step takes place. One that most consumers never think about: anti-clumping treatment. Because McDonald's fries are thin and uniform, they're at risk of sticking together once frozen, especially in high moisture environments. To counter this, a microscopic layer of dextrose is sometimes applied after blanching and before freezing. This coating is not added for sweetness. It's there to assist with color development and minimize the chance of oxidation during storage. It also subtly enhances surface crispness during the final fry. In some factories, an even more specialized process is used. A combination of sodium acid pyrophosphate and citric acid may be sprayed on the fries pre-freezing to lock in that golden hue. This solution prevents enzymatic browning and further stabilizes the fry's color even after months in frozen storage. It's a step that might seem unnecessary, but in the McDonald's system, where fries are shipped internationally and cooked under variable conditions, it's part of the formula for total consistency. Once fully frozen and treated, the fries are transported to the packaging line. This stage is fast, automated, and highly controlled. Fries are weighed using combination scales, which use dozens of small buckets to calculate the perfect load. Whether it's 2.5 pounds bulk bags for food service or 10 pounds cartons destined for regional McDonald's distribution centers. Each batch is fed into high-speed form-fill-seal machines where plastic liners are formed from reels of film filled with frozen fries and sealed airtight. Oxygen is flushed from the bag and replaced with inert gases like nitrogen to extend shelf life and prevent freezer burn. Each bag is labeled with batch codes, facility information, and freeze dates. These bags are then placed into corrugated cartons, which are automatically stacked onto pallets and shrink wrapped. The pallets are scanned into the facility's warehouse management system and stored in vast, temperature-controlled storage rooms maintained at below -10 degrees Fahrenheit. From here, they wait, sometimes just days, other times weeks, before being dispatched to a McDonald's distribution hub. What's rarely discussed publicly is just how advanced the inventory system is. Every pallet of fries is tracked from the moment it's boxed to the moment it's unloaded in a restaurant kitchen. If there is ever a concern about quality, contamination, or shipping damage, McDonald's corporate and their suppliers can trace every fry down to the production line, fryer, and time of day it was processed. This traceability isn't optional. It's embedded in food safety protocols, legal compliance systems, and global quality assurance audits. When the fries finally arrive at a McDonald's restaurant, they're still not done. They are stored in walk-in freezers until ready for use, where conditions must be monitored and logged to ensure the frozen state is never compromised. A fry that partially thaws and refreezes will develop ice crystals, lose crispness, and underperform in the fryer. Every crew member in the kitchen is trained to handle the frozen product delicately, shaking bags to loosen clumps, never overloading the baskets, and minimizing the time between freezer and fryer. And now, the final fry begins. In store, the frozen fries are dropped into preheated oil, specifically a blend of canola oil, corn oil, and soybean oil. However, what most consumers don't know is that this oil is carefully filtered and changed according to a strict schedule. Filtration systems inside each fryer remove particles of carbonized food and prevent oil breakdown, extending usability while maintaining the clean, light flavor McDonald's demands. The oil is tested multiple times daily for free fatty acid levels, color, and foaming to make sure it hasn't deteriorated. If any reading goes outside McDonald's specifications, the oil is discarded and replaced. The frying process in store lasts precisely around 3 minutes at roughly 168-175 degrees Celsius, depending on local settings and fryer model. During this time, the moisture inside the fry flashes to steam, puffing the interior slightly while the exterior rapidly crisps. Those tiny air pockets created by the factory blanching and flash frying now finish the transformation. And the secret to McDonald's uniform texture? It's those pre-engineered starches and exact cook times. When done properly, the fry is lightly golden, stiff enough to hold its shape, and just soft enough inside to match the one you had years ago. Seasoning is also precisely measured. As the fries are shaken from the fryer basket, they're dropped into a stainless steel holding tray and dusted with a uniform dose of pure, fine-grained salt. The salt granules used by McDonald's are specially selected for size and shape, large enough to adhere to the surface oil, but fine enough to dissolve quickly on the tongue. Shakers are calibrated, and portion control guidelines ensure consistency across locations. And here's the last hidden layer of control: the fry holding time. McDonald's dictates that fries must be served within a very specific window after cooking, usually no more than 7 minutes. After that, they're discarded, even if they appear fresh. This strict timer is part of the reason your McDonald's fries are often hot, crisp, and consistent. It's also one of the reasons you'll rarely see a fry sitting under the heat lamp for long. While most McDonald's fans recognize the signature taste of their fries almost instantly, few understand just how orchestrated that flavor really is, or how it's achieved through a global network of tightly controlled suppliers, additive strategies, and ingredient choices designed to replicate a flavor memory baked into the global food consciousness. The story of McDonald's French fries isn't just about potatoes, oil, and salt. It's about manufacturing identity, reproducing the exact same sensory experience for billions of customers each year, regardless of where or when they eat them. To understand how McDonald's does this, you need to look beyond just the factory floor. Behind the scenes is a system of global standardization that governs everything from agricultural inputs to packaging films. Simplot, McCain, and Lamb Weston are the primary suppliers of McDonald's fries, and each operates massive, dedicated processing plants, some of which process hundreds of thousands of pounds of potatoes per day, exclusively for McDonald's. These facilities are synchronized with a global specification book that dictates the required fry length, thickness, shape, sugar tolerance, moisture range, oil absorption, and post-fry texture. And then there's the flavor. Many consumers don't realize that McDonald's French fries are subtly flavored before they ever reach the restaurant. For decades, McDonald's fries were cooked in beef tallow, a rendered fat from cattle, that gave them their distinctive, rich flavor. But by the 1990s, amid rising health concerns and cholesterol awareness, McDonald's phased out animal fats and replaced them with vegetable oils. This change had a major impact on taste, prompting backlash from loyal customers who noticed the difference almost immediately. What most people don't know is how McDonald's responded to that backlash, not by returning to beef tallow, but by recreating its flavor synthetically. Today, the par-fried fries that leave the factory are flavored with a natural beef flavor additive. This additive is applied during the pre-frying stage or infused into the frying oil and contains hydrolyzed wheat and milk derivatives. It's designed to replicate the rich, meaty aroma once delivered by tallow, but without using actual beef fat. This additive is one of the most closely guarded secrets of the entire process. It's what gives McDonald's fries that faint umami backbone that makes them taste savory in a way that purely plant-fried potatoes often do not. And while this additive is labeled as natural flavor on ingredient lists, its composition is highly engineered by flavor chemists and tested repeatedly to ensure it holds up under freezing, frying, and heating conditions in restaurants. The flavor system doesn't stop at aroma. Texture plays a role too. McDonald's fries are engineered to crisp on the outside and remain soft in the middle, and achieving this consistently across markets is an engineering challenge. The crinkle-like effect of the outer skin is partly due to starch modification. Some potato slices are lightly coated with a thin layer of modified starch before freezing, an invisible layer that reacts in the fryer to create a delicate crust, locking in moisture and helping the fry maintain a longer crisp life under heat lamps. This crust is not easily visible, but it is critical. Without it, fries would quickly become limp and oily within minutes of cooking. With it, they hold their shape, resist sogginess, and retain that gentle crunch even as they cool. And although McDonald's does not add batter to its fries, as some fast food chains do, this ultra-thin layer of modified potato starch acts in a similar way, without compromising the all-natural image. Regionally, the manufacturing process must adjust for climate, regulation, and local preference without changing the end result. For example, in India, McDonald's fries do not contain the beef-derived flavoring found in the US to respect dietary and religious restrictions. In Muslim-majority countries, fries may be certified halal and produced in dedicated facilities to ensure separation from non-compliant products. These adjustments require dedicated supply chains, custom formulation runs, and regular taste panels to ensure that the final fries remain indistinguishable from their global counterparts in look, feel, and taste. Flavor consistency is upheld using trained sensory teams who sample fries from different global markets and compare them to reference standards kept in controlled storage. These panels evaluate crispness, oil profile, salt adhesion, internal moisture, mouthfeel, and aroma. If a discrepancy is detected, for example, fries from a factory in Southeast Asia are crispier than those in the US, engineers can investigate and recalibrate oil composition, blanching temperature, or drying time to rebalance the product. And there's more. Packaging. Even the packaging for McDonald's fries is a product of manufacturing science. The familiar red carton is designed not just for branding, but for thermal control and grease resistance. The paperboard is treated with a food-safe coating that prevents oil soak through, and the shape of the carton, with its slightly flared mouth and deep vertical pocket, is calibrated to maintain heat without trapping steam. Fries are less likely to sweat inside these containers compared to traditional closed boxes, which helps preserve texture even during transport or delivery. In the supply chain, those frozen fries move through an equally engineered logistics network. From factory freezers, they're shipped in refrigerated trucks, often under continuous GPS and temperature tracking. Distribution centers store them in walk-in freezers maintained below -10 degrees Fahrenheit, and restaurant deliveries are timed and logged to minimize thaw risk. McDonald's tracks fry inventory down to the store level, forecasting usage based on PCPOS data, and adjusting regional deliveries in real time. If a freezer malfunctions, the system flags the at-risk batch immediately, allowing a preemptive product pull before a customer ever notices. Back in the restaurant, staff are trained using digital timers, fry chart cards, and standardized scoops to portion, salt, and serve the fries. McDonald's restaurants even perform fry station audits to check adherence to hold times, oil filtering frequency, and batch rotation. These audits happen regularly, often without notice, and are tied to store performance metrics. Managers are held accountable for fry quality just as they are for speed of service or cleanliness. Despite all this control, McDonald's fries do have one unavoidable weakness: time. Even with starch systems, flavor additives, and optimized packaging, fries lose their peak texture within minutes. That's why McDonald's limits the hold time in the warmer to around 7 minutes. After that, fries are discarded, still edible, but no longer acceptable by brand standards. This results in significant waste, but it also maintains McDonald's reputation for fresh tasting fries, even if they were frozen and processed weeks earlier. So what are McDonald's factories really hiding? Not deception, not shortcuts, but the scale and precision of industrial food science operating behind something as simple as a fry. The way a potato is selected, how it's processed, flavored, partially cooked, frozen, stored, shipped, fried again, and even salted. All of it is engineered to deliver that one familiar experience. Hot, golden fries that snap slightly when bitten, give way to a tender interior, and leave a subtle beefy aroma in their wake. What they're hiding is just how much work it takes to make something look so effortless. The real secret of McDonald's fries is that there are no accidents. Every element, from starch composition to carton geometry, is designed. And in a world where people crave predictability in their favorite foods, that's exactly the point. The next chapter in McDonald's French fry production isn't just about improving what already exists. It's about redefining how the entire process can evolve under new technological, environmental, and consumer health expectations. While the current system has been fine-tuned over decades to deliver uniformity and mass appeal, the future introduces challenges that can't be solved by simply optimizing old methods. Automation, artificial intelligence, sustainability, and evolving nutritional preferences are all converging to push McDonald's and its processing partners into the next phase of fry manufacturing. One of the most notable developments is the rise of advanced automation and AI-driven process control. In modern McDonald's fry facilities, machine learning algorithms are already being piloted to monitor real-time data from every stage of production. Sensors embedded along the slicing lines, blanches, fryers, and freezers send continuous streams of information: potato dimensions, sugar content, moisture loss, oil flow, fry color, and more. These AI systems analyze the incoming potato crop and dynamically adjust settings like blade calibration, blanching time, or oil temperature to match variations in raw material quality. Instead of relying on preset recipes, the system now learns and adapts, helping reduce inconsistencies and food waste. In parallel, robotics are making inroads not just in manufacturing, but inside McDonald's restaurants themselves. Frying stations in pilot stores are being equipped with robotic arms or automated baskets that load, cook, and shake fries with no human input. This standardizes cook time and reduces operator error, ensuring that each batch is fried exactly to spec, regardless of shift or staff turnover. For McDonald's, this reduces labor costs, improves food safety, and eliminates variability in fry texture and temperature. Sustainability is also driving significant changes. One of the key pressures on the current model is oil usage. While McDonald's already employs rigorous oil recycling and filtration protocols, new systems are being trialed that extract even more particulates and extend oil life significantly without affecting flavor. Some suppliers are exploring high-efficiency fryers that use vacuum environments to lower frying temperatures, reducing oil absorption and energy usage. McDonald's is also quietly funding research into lower oil par-frying methods that could replicate crispiness using air-based thermal systems, potentially paving the way for a future where fries are air-fried in-store rather than deep-fried. Water usage is another sustainability frontier. The massive amounts of water used in washing, blanching, and rinsing potatoes are being addressed through closed-loop recycling systems and precision spray technologies. Instead of full immersion, some newer systems use high-pressure misting to clean and treat potato surfaces, cutting water usage by up to 40% per ton of potatoes processed. Every gallon saved matters when facilities are producing millions of pounds per week. Health consciousness among consumers is also influencing the future of McDonald's fries. Although the company has already shifted to trans fat-free oils, the next step may involve reducing sodium or introducing new seasoning options. Internally, there's ongoing experimentation with lower sodium salts that maintain the same flavor perception with less actual sodium chloride. Other ideas under consideration include sweet potato or blended vegetable fries, though any change to the core offering would require monumental testing to avoid alienating loyal customers. Few snacks on the market capture the attention of consumers quite like Takis. With their signature rolled shape, vibrant colors, and explosive spicy flavors, Takis have carved out a unique space in the world of extruded corn snacks. Originally created by Barcel, a Mexican subsidiary of the Bimbo Group, Takis have grown from a regional novelty to a global snacking sensation. But behind each intensely flavored bite is a fascinating and highly engineered manufacturing process that brings together agricultural science, mechanical precision, and food chemistry on a massive industrial scale. To understand how Takis are made in a factory, we must begin at the very first stage, the sourcing of raw materials. The cornerstone ingredient in Takis is corn, more specifically, degermed corn flour, often referred to as mesa flour. This flour is derived from yellow or white field corn, grown primarily in the United States and Mexico. The corn used must meet specific quality parameters, particularly in terms of kernel size, moisture content, and starch composition. Contracted farmers typically grow this corn under strict agronomic practices to ensure high yield and consistent quality. Once harvested, the corn is transported to centralized milling facilities, where it undergoes a critical transformation. This transformation begins with the nixtamalization process, a traditional method that dates back to ancient Mesoamerican civilizations. In modern milling operations, dried corn kernels are steeped in a lime water solution, water mixed with food-grade calcium hydroxide at controlled temperatures for several hours. This chemical soaking loosens the hulls, softens the kernels, and alters the protein and carbohydrate structures, improving both flavor and digestibility. Once steeped, the corn is thoroughly washed to remove residual lime and loosen pericarp. What remains is nixtamalized corn, which is then ground through industrial stone mills or hammer mills into a fine, homogeneous masa dough. For Takis, however, the mesa is taken one step further. Instead of being used wet, as in tortilla production, it is dried and ground again into a shelf-stable mesa flour. This dried masa, now fine and moisture-free, serves as the primary input in the Takis production process. It's stored in massive silos within the factory, equipped with aeration systems to keep the flour dry and flowing freely. Pneumatic conveyors transfer the flour to precise metering hoppers above the mixing equipment. Here is where the transformation from flour to snack begins in earnest. The masa flour is dropped into high-capacity industrial mixers, where it is blended with water and a proprietary mixture of seasonings, emulsifiers, and sometimes oil. These mixers are equipped with temperature control systems and paddles designed to evenly distribute moisture throughout the blend. The goal is to create a pliable yet firm dough that is suitable for extrusion, a process that will ultimately define the iconic Takis shape. The mixed dough is conveyed directly to the extruder, a high-pressure, high-temperature piece of equipment that lies at the heart of many snack food manufacturing lines. For Takis, a twin-screw extruder is typically used. The dough is fed into the extruder barrel, where rotating screws push the material forward while simultaneously mixing, shearing, and heating it. Inside the barrel, steam pressure rises dramatically due to intense friction and controlled moisture. This heat gelatinizes the starches within the mesa, turning the dough into a malleable, semi-cooked matrix. At the end of the extruder barrel lies a die plate with specially engineered openings. These dies are shaped to produce flat ribbons of mesa with uniform width and thickness. As the dough exits the extruder, it experiences a sudden drop in pressure, causing it to puff slightly, though not excessively, as takis are denser and more compact than puffy snacks like cheese curls. Automated blades then cut the ribbons to a standardized length, usually between 4 and 6 inches. Now comes one of the most recognizable steps in the process, the rolling. Using a synchronized series of mechanical arms and belt-driven rollers, each flat strip is quickly rolled into a tight cylinder, mimicking the appearance of a small, rolled taco or taquito. This is done at high speed, often in under a second per piece, with careful calibration to prevent unrolling or uneven shapes. The rolling units must operate with precise timing and alignment, as even small inconsistencies could result in defective product or downstream clogging. Once formed, the raw takis are transferred onto a mesh conveyor belt that carries them into the continuous fryer. Unlike air-puffed snacks, takis achieve their final texture and flavor through frying in hot oil. The frying process occurs in large stainless steel fryers filled with high-stability vegetable oil, typically corn or sunflower oil. The oil is maintained at a consistent temperature, usually around 350 degrees Fahrenheit, and is constantly filtered and replenished to maintain quality and prevent flavor degradation. As the takis pass through the fryer on a conveyor, they cook rapidly, the exterior crisping while moisture evaporates from the interior. This gives takis their signature crunch, dense and satisfying, with just enough resistance to offer a unique mouthfeel. The fry time is carefully controlled, usually around 30 to 60 seconds, to ensure even cooking without burning or excessive oil absorption. Temperature sensors, oil flow meters, and automated timing systems monitor every batch, with defective products automatically rejected by vision systems downstream. As soon as they exit the fryer, the takis must be cooled rapidly to halt cooking and prepare them for seasoning. The hot snacks are dropped onto a vibrating cooling conveyor, which uses forced, ambient, or chilled air to bring their temperature down quickly. This conveyor system not only cools, but also aligns and spreads the product evenly, preventing clumping before seasoning. And this is where the flavor magic happens. Takis are famous for their bold and intense seasoning blends, most notably the Fuego variety, which combines hot chili pepper and lime. The cooled snacks enter a large rotating tumbler or flavor drum, where they are coated with a fine mist of oil or flavor adhesive, such as maltodextrin or gum arabic. This light coating ensures the powdered seasoning sticks uniformly to the surface. Then, a precisely metered amount of dry seasoning blend is sprayed onto the rolling takis within the drum. The tumbler rotates at a controlled speed, ensuring that every piece receives an even coating of the intensely red, flavor-packed powder. The powder itself is a carefully engineered blend of spices, acids, artificial flavors, and colorants, many of which are micro-encapsulated to preserve potency until consumption. This step is where flavor engineers shine, crafting bold profiles that hit the palate in waves. First, the citrusy tang of lime, then the slow-building burn of capsaicin from chili powder, followed by savory umami notes and salt. Once the takis are evenly coated with their signature seasoning, the product advances to the post-seasoning inspection stage. Here, Quality control takes center stage. As the finished snacks move down the conveyor belt, they pass through a combination of optical sorters, weight sensors, and human oversight stations. These systems are tasked with identifying any irregularities, broken pieces, improperly seasoned rolls, or foreign particles. High-speed cameras analyze each item against a programmed standard, with air jets used to automatically divert defective snacks from the production line. This meticulous approach ensures uniformity in every batch, both in appearance and taste. After clearing inspection, the freshly seasoned Takis enter the final phase of the production process: packaging. In large-scale manufacturing operations, packaging is not merely about enclosing the product in a bag. It's a tightly orchestrated, high-speed operation designed to maintain freshness, ensure food safety, and optimize shelf life. The cooled Takis are funneled into hoppers that portion them into individual servings. These hoppers are mounted above form-fill-seal machines, or FFS machines, which are the heart of the packaging operation. Each FFS unit starts with a continuous roll of multi-layered packaging film. This film is typically made from a combination of materials such as polyethylene, aluminum, and polypropylene. These layers provide essential barrier properties, keeping out oxygen, light, and moisture, elements that would otherwise degrade the snack's flavor and texture. The film roll is unwound, shaped into a tube, and sealed along its vertical edge using heat sealing bars. Simultaneously, the bottom of the tube is sealed to form a pouch, into which a precise dose of Takis is dropped from the hopper above. As the filled pouch moves through the machine, a horizontal seal is applied at the top, closing the package and completing the bag. The result is a perfectly sealed, shelf-ready snack pouch. Some facilities also inject an inert gas, typically nitrogen, into each bag before sealing. This process, called nitrogen flushing, displaces oxygen and helps prevent oxidation of the oil and spices inside the snack. It's a key technique in preserving freshness for weeks or even months after production. But the packaging line doesn't stop there. Once sealed, the Takis bags are conveyed to the labeling and coding station. Here, high-speed inkjet printers apply critical data to each bag, including production date, batch code, and expiration date. These codes are essential for traceability, enabling both the manufacturer and regulatory bodies to track products through the supply chain and, if necessary, initiate a recall. In larger factories, barcode scanners validate each print in real time, flagging any unreadable or incomplete prints for immediate rework. Next, the finished snack bags are grouped into larger quantities for secondary packaging. Robotic arms equipped with suction grippers or mechanical claws pick up batches of bags and place them into cardboard cartons or shrink-wrapped bundles. These secondary units are ideal for distribution to retailers, vending machine suppliers, and food service channels. Automated case erectors, packers, and palletizers handle this stage with minimal human intervention, ensuring consistency and speed. Once boxed, the cartons are scanned one final time, then transported to the warehouse using automated guided vehicles or conveyor systems. The warehouse itself is climate controlled, maintaining ideal conditions for snack storage, typically around 70 degrees Fahrenheit and low humidity. Inventory management systems track every pallet, integrating with enterprise resource planning software to coordinate distribution across multiple regions and customer channels. At this stage, Takis are officially ready for distribution. Depending on the destination, pallets may be routed to regional distribution centers, export facilities, or directly to major retailers. In the US, this typically involves refrigerated trucks or dry vans with temperature and humidity monitoring systems to ensure the product remains in peak condition throughout transport. For international shipments, Takis are loaded into containers and shipped via freight lines, with each load accompanied by customs documentation, certificates of analysis, and food safety verification records. It's important to note that all these stages, milling, extrusion, frying, seasoning, packaging, and shipping, operate under strict regulatory compliance and food safety protocols. The Takis manufacturing facility is typically audited regularly by health authorities and third-party certification bodies to maintain good manufacturing practices and adherence to standards such as the Global Food Safety Initiative. HACCP, or hazard analysis, and critical control points is implemented throughout the line to identify and mitigate risks, from biological contamination to mechanical hazards like metal fragments. Metal detectors and X-ray machines are also integrated into the production line post-frying and pre-packaging. These systems serve as a critical control point, scanning every product to detect foreign objects that could compromise consumer safety. In the rare event a contaminant is found, the system immediately shuts down the line and activates traceability protocols, ensuring the source of the contamination is quickly identified and corrected. In addition to food safety, automation plays a crucial role in the consistency and scalability of Takis production. Modern factories are outfitted with CAD systems, supervisory control, and data acquisition, which allow operators to monitor and adjust every part of the process in real time. Temperature readings, fry times, dough consistency, seasoning distribution, packaging integrity, all of it is visible from centralized control rooms staffed by trained technicians. These systems also gather historical data, enabling predictive maintenance and process optimization over time. Moreover, the human element remains vital. Quality assurance personnel regularly conduct sensory evaluations to ensure the finished product matches the flavor, aroma, and texture profile that consumers expect. Samples are pulled at set intervals and subjected to detailed analysis, including moisture content testing, oil content analysis, pH measurements, and microbial testing. These assessments help maintain product consistency and detect any early signs of spoilage or variation. And let's not forget the environmental impact. Many modern snack food factories, including those producing Takis, are actively investing in sustainable practices. Waste heat from fryers is often reclaimed and used to preheat water or air elsewhere in the facility. Oil used in frying is filtered and recycled several times before final disposal. Packaging materials are increasingly being sourced from recyclable or biodegradable films, and energy-efficient motors and lighting systems reduce overall factory emissions. The success of Takis also hinges on innovation. Flavor development is a continuous process involving food scientists, sensory analysts, and marketing teams. New flavors are often trialed in small-scale batch lines within pilot plants, where formulation tweaks can be made rapidly without disrupting full-scale production. Once a new variety passes consumer testing, it's scaled up to the main line, where production parameters are adjusted to accommodate the unique characteristics of the new seasoning blend. In essence, every bag of Takis represents a fusion of ancient techniques and cutting-edge food science. From the Mesoamerican tradition of nixtamalized corn to the robotic arms and AI-controlled inspection systems of a 21st century factory, the journey from cornfield to snack aisle is a marvel of industrial engineering. The attention to detail, the layers of safety checks, the complex choreography of machines, and human oversight all come together to create that iconic crunch and fiery kick that snack lovers around the world have come to crave. Once the freshly sealed Takis packages leave the manufacturing floor, their journey is far from over. The next phase, post-factory logistics and storage, is just as critical to the integrity of the final product. From the moment those pallets are loaded onto the loading docks, every step must be meticulously orchestrated to maintain freshness, comply with regulatory requirements, and meet retailer timelines. Palletized shipments of Takis are typically staged in designated outbound logistics zones within the factory's warehouse. Here, inventory management systems, integrated with warehouse management software, guide automated forklifts or human operators in sequencing outgoing loads. Each pallet is tagged with RFID or scannable barcodes, providing traceable data like batch number, production date, customer destination, and handling instructions. This is especially vital in high-volume operations where hundreds of thousands of units move through daily. Distribution of Takis often begins with transfer to regional distribution centers, or RDCs. These massive hubs serve as strategic points between the manufacturing facility and the retail shelf. Transportation is conducted via trucks equipped with climate control systems to protect the product from temperature spikes or humidity, both of which could compromise the texture and flavor of the highly seasoned snack. Although Takis are non-perishable, they are still sensitive to environmental conditions due to the oil content and delicate nature of their fried, rolled structure. Upon arrival at RDCs, the pallets are unloaded and sorted according to their final destination. Some may be earmarked for export, requiring additional customs documentation and compliance with international food labeling standards. For domestic markets, the focus shifts to inventory allocation, wherein Takis are divided among retailers based on demand forecasts, sales trends, and marketing campaigns. Algorithms calculate optimal shipping routes and timelines to minimize storage time and maximize shelf life for consumers. In-store delivery typically occurs on a just-in-time basis. Retailers prefer to receive snack shipments shortly before they are needed for shelf restocking to reduce their own warehousing costs. Specialized delivery trucks make daily or weekly runs to supermarkets, convenience stores, gas stations, and even vending machine distributors. Each of these retail environments poses unique packaging and merchandising challenges, all of which were anticipated back at the design and branding stage of the Takis production cycle. One of the unsung heroes in the journey of Takis is the shelf life optimization strategy. Although the product is fried, which naturally reduces moisture content and microbial activity, the seasoning powders and oils are susceptible to degradation over time. To combat this, manufacturers employ a suite of preservation techniques. Nitrogen flushing, as mentioned earlier, displaces oxygen in the sealed package, but antioxidants like tocopherols or rosemary extract are often blended into the seasoning to prevent rancidity. Additionally, desiccant sachets are sometimes included in bulk packaging layers to absorb ambient moisture during long-haul shipping. Once Takis make it to the retail environment, product rotation and visual appeal become the next critical concerns. Merchandising teams work with stores to position Takis in eye-catching locations, often near checkout counters or in custom display racks. Packaging design plays a crucial role here. The vivid purple of the Fuego flavor, for instance, has become iconic. This is not accidental. It is the result of extensive consumer psychology research and competitive shelf analysis. The packaging is printed using high-intensity inks and UV-cured varnishes that resist fading under fluorescent retail lighting. Meanwhile, behind the scenes, the manufacturer continues to monitor product performance through various feedback loops. Point-of-sale data is constantly reviewed to identify hot-selling regions, seasonal trends, and underperforming SKUs. Social media sentiment analysis and direct consumer feedback also guide adjustments in flavor intensity, packaging size, and promotional strategies. All of this feeds back into the product lifecycle management software, which helps guide future production and flavor development decisions. Speaking of flavors, one of the most fascinating aspects of the Takis operation is the flavor innovation pipeline. Flavor development is not merely a matter of combining spices. It's a complex interplay of sensory science, market forecasting, and precision engineering. Within dedicated R&D facilities, flavor scientists and food technologists explore new seasoning blends that push boundaries while remaining accessible to a wide audience. Using a combination of gas chromatography, mass spectrometry, and trained sensory panels, they deconstruct flavor experiences into measurable data points. For example, developing a new flavor like Dragon Sweet Chili or Blue Heat begins with identifying flavor trends in regional and global markets. Are consumers leaning toward Asian-inspired profiles? Are younger audiences seeking spicier, more adventurous options? Once a flavor theme is chosen, food scientists begin formulating dry seasoning blends that meet those goals. These blends are then micro-encapsulated to maintain potency through the frying process, ensuring that the end product retains its flavor intensity after months on the shelf. Prototypes are created on small-scale extrusion and seasoning lines within pilot plants. Here, the entire Takis production process is simulated at a reduced scale. This allows for rapid testing of texture, color retention, seasoning adhesion, and oil interaction without interrupting full-scale operations. Multiple iterations may be required before the formula is finalized. Once approved, the new flavor is scaled up and introduced into the market through limited releases or promotional campaigns. Based on consumer reception, it may join the permanent lineup or serve as a limited time offering. But with every new flavor comes new challenges. Seasoning powders vary in density, oil absorption, and electrostatic properties, all of which affect how they adhere to the snack. The tumbler rotation speed, spray nozzle angle, and even drum temperature may need to be recalibrated to accommodate different blends. For spicy varieties, capsaicin levels must be carefully controlled not only for flavor balance, but also to comply with regional regulatory thresholds for spice labeling. Some jurisdictions require heat warnings if the Scoville rating exceeds a certain level. Furthermore, regulatory compliance is a continuous effort in every phase of production. Labels must accurately reflect ingredients, nutritional values, and allergens. In countries like the US, compliance with FDA labeling laws is mandatory. In the European Union, Takis must also adhere to FSA food additive regulations and translation requirements. This means each regional variant may have slightly different formulations or packaging to meet local standards. Another area of innovation is sustainability. Snack food factories around the world are under increasing pressure to reduce their environmental footprint. The Takis production chain is no exception. Some facilities have introduced biodegradable packaging options for select markets, while others have invested in solar panels and high-efficiency fryers to cut energy use. Spent cooking oil is now commonly collected and converted into biodiesel, and water used in nixtamalization is filtered and reused for non-contact applications like equipment cooling. Sustainability also intersects with supply chain ethics. Corn suppliers are vetted not only for quality and price, but also for compliance with labor and environmental standards. Supplier audits are conducted regularly, and digital traceability platforms are used to map the corn's journey from field to fryer. This level of visibility allows the manufacturer to ensure that every ingredient in a Takis snack aligns with their corporate responsibility goals. Takis, for all their fiery boldness and snackable appeal, are a masterclass in food engineering and global logistics. They represent what happens when cultural flavors are married with advanced manufacturing, when age-old ingredients are given new life through extrusion science, and when every detail, from the grind of the corn to the curve of the roll, is tuned for maximum consumer satisfaction. As the Takis brand continues to evolve, the role of emerging technology in snack production becomes increasingly pronounced. Digital twins, for instance, are now being introduced in advanced food manufacturing environments. These are real-time digital replicas of the physical production line, complete with sensors, predictive analytics, and machine learning algorithms. By modeling the entire extrusion and frying process digitally, operators can simulate how small changes in variables, such as dough moisture content, oil temperature, or seasoning particle size, will impact the final product before making physical adjustments. This minimizes downtime, reduces waste, and enhances consistency across batches. Artificial intelligence and machine vision systems are also revolutionizing quality control. High-resolution cameras paired with deep learning algorithms can now detect subtle flaws that human inspectors might miss, such as uneven seasoning, microfractures in the rolled snack, or variations in color that could indicate improper frying. These systems learn over time, refining their detection capabilities with each batch they analyze. This not only improves product quality, but also enhances traceability and accountability within the plant. One particularly forward-looking development is in the realm of alternative ingredient sourcing. As demand for gluten-free, vegan, and allergen-free snacks continues to rise, food scientists are exploring reformulations of Takis that use alternative flours, such as chickpea, lentil, or sorghum flour. These flours come with their own extrusion challenges, especially when it comes to texture and structural integrity. Specialized extruder screws and preconditioning treatments may be necessary to match the crispness and density of the original corn-based recipe. Flavor delivery is another frontier being actively developed. Microencapsulation technologies are growing more sophisticated, allowing for flavors to be released sequentially as the snack is chewed. This creates a dynamic sensory experience, perhaps a burst of lime, followed by a wave of chili heat, then a subtle, lingering smokiness. These multi-layered flavor profiles are tested rigorously in consumer panels and sensory booths, with metrics like aftertaste duration, palate burn intensity, and residual coating all logged and analyzed. All these innovations are feeding into a broader trend: personalization. The concept of mass-customized snacks, where consumers can choose their preferred heat level, flavor intensity, or seasoning combo, may soon become viable thanks to modular production lines and just-in-time mixing systems. Imagine entering a vending machine interface or online store where you could build your own Takis variant, which is then mixed and packed to order within minutes.